Uh, at first, I welcome Professor Ranjan Ganguly at the digital platform of JBNSTS. During last 4 months almost, we are organizing regular seminars for our scholars. In earlier times, we organized some lectures from doctors and from medical persons, from biologists that were mainly focused on COVID situation, the molecular biology of COVID, how to test the COVID, how to form the vaccine, this type of lectures. But you know that basic science and engineering makes a joint platform to take the challenge of the society. And that is the most relevant thing. In that perspective, we invited Professor Ranjan Ganguly because in earlier times, whenever we listened to his lecture, always it was a very good application to solve the real life problems. And Professor Ranjan Ganguly is a renowned professor at Jadavpur University. He has an excellent profile. I will tell you the profile because you will be inspired to know that he was a brilliant student in Jadavpur University from Department of Power Engineering. He did his master's also there. After that, he did his PhD in University of Illinois at Chicago. Still now, he's the adjunct professor at that university. Then he went for his postdoctoral work, Virginia Tech, then also TC of Technological University of Darmstadt, and several other reputed university. He is a Humboldt scholar. That is also another very exciting thing. He's a member of National Academy of Engineering, and he had many accolades in his reserve, and he was awarded with several medals and scholarships. He leads a large research team, and he is also renowned for his as a student-friendly teacher. So I think we are all waiting for his exuberant presentation that will inspire all of you. And after his lecture, definitely we will go for a discussion session. So thank you very much, Professor Ganguly. I invite to start your lecture.
Thank you. Thank you, Dr. Ganguly.
Thank you, Moitridi, for this kind introduction. And very good morning to all of you. I would request Dr. Abhijit Kaur to give me a ring on my phone whenever there is a technical glitch. And I mean, you lose me over connection or you don't hear my voice. So again, a very warm welcome to all of you. Moitridi gave an illustrious introduction of mine, but what she didn't tell me is that I am not a JB scholar. Actually, I couldn't make it to the JBNSTS scholarship in the final round. So you can easily guess that you are already on a platform above me. So whatever you have heard about my CV, that's the baseline. You will definitely soar much above that. So my job is to just to give you some excitement to the science and some motivation with one example of some scientific pursuit which we are pursuing in order to solve some practical problem in our life. Now, I will start with a favorite slide of mine, although it's kind of outdated in the very present context. But it originated from a Nobel laureate, Sir Richard Smalley, who won Nobel Prize in '96. And in a 2004 lecture made in Washington, D.C., he identified the top 10 global challenges, and he ranked them in the order of priority. And as you can see that energy and water at the top two, as he identified as the top two global challenges. And on the number 7, you can identify diseases. But of course, in the present scenario, everybody will jump from your seats and say that right now, this is the number 1 problem that we are facing. But if you think very carefully, over a span of next 50 years, I mean, 50 years started from 2004, if you really integrate all the challenges over time, you will probably still find that energy and water are at the top. This number 7, the spike in the number 7, which has like brought the entire world at their knees, is probably going to pass soon. And still this number 1 and 2 are going to prevail. So that's why we try to address some of the problems that are related to energy and water. And we call it energy-water nexus because these two are intricately related. And what I mean by a skin-deep approach is not a superficial, a casual, but something which we can address by simply altering the surface property of the materials. So, looking at the energy and water problem, the water problem, for example. And talking about water problem, we all are familiar with scarcity of water, particularly in desert areas. And talking about desert, I would like to remind you of this region on the planet, which is called Namibia. And the Namib Desert is one of the most arid part of the entire world. It receives a paltry rainfall of 2 to 200 millimeters in a year, and the temperature hovers around 9 to 20 degrees Celsius. Despite there is a very peculiar natural phenomena that takes place in this desert. For a period of like 60 to as high as 200 days in a year, it receives what is known as morning fog, a dense morning fog that comes from the ocean, and it sweeps over this desert. There is no rain, but there is fog. And this tiny little creature in that desert utilizes this occurrence. These are called Namib desert beetle. There are a few number of these Namib desert beetle, but the beetle that I'm talking about is known as Onimatrisongacularis, and they are known as fog basking beetle. What they do is like they come up in every morning from their holes in the sand dunes where they bask at night, and in early morning they come out and go to the top of the dunes, assume a pranama position like this, facing the fog, which you can see on the top left image with the arrow direction shows the direction of the fog. And they just stand still like that for hours. Water collects on their back, it drips down their back, goes to their mouth, it entirely wets their body. And they can collect up to 12% of their body weight. When you look closely, they have on their back a hard shell, which we call elytra. And this elytra has tiny little ridges, and it has a strange wettability, meaning that the tendency of water adhering to the surface, which allows them to collect the maximum amount of it. And it's not only these beetles, but also there are some other plants in desert which the scientists have noticed that they have certain features on their leaves which allow them to collect water, whatever amount they receive in the form of the fog from the atmosphere. For example, this Bushman grass, they have ridges on their surface, and under a scanning electron microscope, one gets to see roughness features, and there are some specific contact angles that a water droplet makes on them. We will talk about these contact angles in a bit later, but they have certain affinity towards the water, which collects on these rough surfaces, and they eventually roll down the leaves, go to the roots, because the grass although it collects the water from the fog through its leaves, the water is uptaken through the roots, so the water drains down to their to the bottom, and through the root they take up the water. And these plants can collect up to 4 to 5 liter per fog event, which is almost 5 liter per meter square per day. If you have like 1 meter square total leaf area, you can collect about 5 liters, 5 full 1 liter bottle of water per day from the fog itself. A pretty decent amount. So this gives us a very interesting natural example of how we can collect water or harvest water from nature. Remember, these plants and the Onimatrisongacularis beetle, they don't spend additional energy to catch this water. So by, not spending much of energy, maybe we learn from nature how to harvest water in the least energy intensive manner. Of course, we saw that there was some magic on their surfaces, the surface of the elytra or the surface of the leaves. So we focus our attention to the surface phenomena. And just to give you like some brief background, probably many of you know about these, but for the sake of general audience, I will quickly gloss over some basic features of surface phenomena. As we all know, any liquid, so to speak, even solids, they have a property known as surface tension. And this surface tension basically arises from the asymmetric force arising on the molecules at the boundaries of their phases. So it's like in a crowded train, when you are inside, you are pushed by all your neighbors and you are staying at the same position. But suppose, imagine yourself hanging at the door of the train. In a crowded train, anybody who commutes from, by local train in Sialda or Howrah, they would know that when the train takes a turn, it leans on one side, and the person sitting on the door shouts that, "Pore jabo, dada bhetore jan." That's because of the push that he gets from one side. The same thing happens for the molecules. Instead of pull, the molecules pull themselves, and the molecules that are on the edge of the phase, they are pulled only by the molecules on the inner side, which means they are having a net unbalanced force which holds them close to the phase side, and that gives rise to the surface tension. And this surface tension gives rise to different shapes of liquid. Like we know that a small liquid droplet takes the shape of a sphere to minimize the total surface area so that the surface energy is minimum and the liquid droplet is in its most energetically favored state. Before we knew this phenomenon of surface tension, nature and its elements knew that. These water striders knew that, the ants knew that, the trees knew that. Now we are slowly learning the intricacies of surface tension. So in the common pedagogy of surface tension, when a liquid is deposited on a solid surface, we find that the liquid stays in a hemispherical form, and it subtends an angle theta with the surface of the solid. So in presence of gas G, solid S, and the liquid L, there is an angle theta made through the liquid phase by the interface between the liquid and the gas and the interface between the liquid and the solid. If you balance the forces right at the contact point, probably you can see my mouse or cursor here, then you get what is known as the Young equation, which essentially relates the surface forces appearing between the solid and the gas, solid and the liquid, and the liquid and the gas. And the surface forces are basically surface tension multiplied by the length that over which they are computed. And the contact angle which is also known as the equilibrium or sessile droplet contact angle, is represented in terms of the surface tensions of the solid, the surface tension between the solid and the liquid, and the surface tension between the liquid and the gas. The gas subscript is omitted here, but these surface tensions basically means the surface energy per unit area. And depending upon the surface energy of the solid or the liquid in gas, we see different behaviors of the liquid droplets on the solid. For example, on the top, you see 4 instances where A shows an event where the liquid, when deposited on the solid surface, spreads widely. If, for example, you take a very clean and highly polished glass and you put a drop of water, the water will spread. The contact angle that you see there is almost 0. It's less than 10 degrees many a times. Generally, if the contact angle is between 0 to 20 degrees, we call them superhydrophilic. If you deposit water on a very shiny metal, say like aluminum, probably you will see a contact angle of around 80 degrees or 70 degrees, depending upon the type of the metal and the alloy that you are using and the liquid surface tension. And in that case, if the contact angle is between 20 to 90 degrees, we call them hydrophilic. Philic means loving. So in A or B, the surface actually loves water. On the other hand, if you take a surface, suppose a wax-coated glass surface, you will see that the contact angle is greater than 90 degrees. And any contact angle between 90 and 150, we call the surface to be hydrophobic. Phobic means it hates the water, so it doesn't like water. On the other hand, there are cases where the contact angle is even higher than 150 degrees. Between 150 and 180, if the contact angle is observed between these two values, we call the surface superhydrophobic. And nature has also given us enough examples of all these 4 types of surfaces. Starting from the lotus leaf, for example, you have the superhydrophobic surface. Other sorts of like plants, you have these leaves which are giving you not greater than 150, but between 90 and 150 contact angle. We call it hydrophobic, hydrophilic, or even there are leaves where you put a drop of water and it spreads like hell. In fact, how it will spread, the liquid will spread also depends on the surface tension of the liquid. So many of you, if any of you are studying agriculture, you probably know that when you want to put spray a pesticide, you want the tiniest, smallest amount of pesticide droplet to spread over the entire leaf. So they put something known as surfactant with the liquid droplet. And in that case, that reduces the surface tension of the liquid, which means that a surface which is hydrophobic otherwise, meaning that it is giving you a contact angle greater than 90 degrees, if you have a droplet of water dispensed on the surface, the same surface will give you a very low contact angle if the liquid is surfacted, means you have surfactant on it. Soap is an example of surfactant. There are several other surfactants which can lower the surface tension of the liquid, which means if the surface tension of the liquid is low, then that can also reduce the contact angle. A superhydrophobic surface generally also offers a very low hysteresis, meaning that when you want to move the droplet or you tilt the surface little bit by gravity, it very easily sheds down. By contact angle hysteresis, what we mean is that our common experience also says that if we have a stubborn surface where it's kind of difficult to get rid of water, if you have a surface horizontal, the liquid is dispensed and it takes equal or it subtends equal contact angle on either side. Then you tilt the surface, the liquid kind of takes an asymmetric shape and you have 2 different contact angles on the advancing side and on the receding side. We call this lower one advancing because if you tilt the plate further, maybe the droplet will start sliding down. And then in that case, this side becomes advancing side and the other end becomes the receding end. And till the moment the liquid droplet actually doesn't slide down, we clearly see that there is a difference between the contact angle on the advancing and receding fronts, which actually arises because of adhesion between the liquid and the solid, and gives rise to a net force which kind of prevents motion of the liquid droplet over the surface. In this case, for example, if you draw a free body diagram of this liquid, you will definitely find a component of the weight tries to move the liquid down the plane, but that is still stuck, or it's holding on the plate because of the net unbalanced surface force because of the contact angle hysteresis. So a higher contact angle hysteresis means that you need to put more force on this liquid to move it over a surface. And the difference between the advancing and the receding contact angle is known as the contact angle hysteresis. It's seen that the liquid, when it moves, depending upon the velocity of the liquid droplet over the surface, the contact angle hysteresis also increases a little bit. Now, talking about the surface tension of the solid, we also find that there are ways to tune the wettability of a solid surface. Because I mentioned that a glass surface, if you clean it by ethanol or spirit and then put a drop of water, it spreads. But if you put a very thin layer of wax on top of it, it doesn't wet. It becomes hydrophobic. Why? Because the coating of the wax has something which repels the water. Basically, the surface tension on the interaction between the liquid and the solid, if you have water and maybe glass, you have the interaction of hydrogen bonding or the van der Waals interaction. Whatever be the case, there is interaction, and depending upon the nature of the surface, the interaction varies, and therefore the water-loving or water-hating nature, or the hydrophilicity and hydrophobicity also changes. It's known that materials like Teflon or fluorinated hydrocarbons, you have a tendency of water repulsion. And that's why we have non-stick cookware, the non-stick pan, where we have a coating of Teflon, which actually repels not only water. They claim that it tries to repel oil also, and it tries to repel any other material, the watery cooked substance, so that it doesn't stick to the surface. So the bottom line is that we can surely treat the surface of a material irrespective of its bulk nature. So we can modify the surface so that its affinity to water can be changed. How do we do that? There are several processes. Like we can dip coat the material. If you have a piece of glass, you can dip coat it in molten wax and pull it up at a definite speed to control the level or the thickness of the wax layer. It's not only the wax. You can coat many other things on glass. You can coat other things on metal. There are different techniques like plasma deposition, vapor deposition. You can do adhesive coating, so on and so forth. Now, apart from surface energy level by coating, or rather which you can tune by coating the surface with some other materials, surface roughness is also another important parameter, because if the surface has a roughness feature, that also alters its affinity towards the liquid. What you see on the top are two states of liquid. One is known as Wenzel state, the other is known as Cassie-Wexter state, which kind of dictates what the apparent contact angle will be, which tells us that if, for example, theta is the contact angle on a smooth surface, suppose you have a glass surface, and on a smooth glass surface, water makes a contact angle of 20 degrees. And the surface has a roughness feature R. The value of R is actually the actual surface area divided by the projected surface area, means that you have on an actual surface area the roughness height. So it's simply, if you have a triangular shape, it's the total length of the hypotenuse, and in the projected surface you have the length of the base. Obviously, the sum of the two other sides of the triangle will be greater than the length of the base. So R, the value of R is always greater than 1, the roughness ratio. And if you just plug in a value of R greater than 1 on cosine theta smooth, the theta smooth is 20 degree, you will find that you get a theta rough which is smaller than theta smooth, which means that the moment you make the same glass surface rough, instead of 20 degree, now the contact angle will drop down to maybe 5 degrees. If the surface is in a Casey-Baxter state, which is more usually observed in a superhydrophobic surface, then you have a strange scenario. Suppose you take this image on the left, you have on a lotus leaf a liquid droplet, a water droplet. What you will see is that there are roughness features on the lotus leaf. There are tiny little fibrous network that protrudes out of the leaf, and there are air layers trapped between the leaf or between the two such strands, and the water actually sits on top, touching only the tip of the fibers, and there is air underneath. And that's why when you see from the top, you will see a shiny surface at the bottom of the water because of the total internal reflection occurring at the interface of the liquid and the gas, the entrapped gas. And under that condition also, the apparent contact angle will be different from the actual contact angle, and that will depend upon what is known as the solid fraction. The phi s denotes actually the amount of it's basically the fraction of the total projected surface area that has solid element. And depending upon the value of the intrinsic contact angle and the solid fraction, the choice of the Casey-Baxter or Wenzel states are actually decided. In a Wenzel state, what you have is that the same surface will actually, the water will impel through the crevices and you will get a full wetting of this liquid. Obviously, a Casey-Baxter state is more agile because the tethering or the adhesion between the liquid and the solid will be less because there is a air layer between or a gas layer between the liquid and the solid, whereas a Wenzel state is stubborn. Nature gives us again two examples of this Casey-Baxter and Wenzel. By the way, Casey-Baxter state is also known as fakir state, which is somewhat analogous to this fakir sitting on the pin cushion. Here the droplet sits on such a scenario in such a configuration. And for example, if we take the lotus leaf, it is in the Casey-Baxter mode. And if you take the rose petals, they are on a Wenzel state. And that's why you will find that if there is a water droplet on a rose petal, it still gives you a very high contact angle, although it doesn't get dislodged very easily, unlike the lotus leaf. So you have a Wenzel state superhydrophobic surface and a Casey-Baxter state superhydrophobic surface. In fact, whether the liquid droplet will stay in the Casey-Baxter mode or Wenzel mode depends upon the surface roughness. And this surface roughness, basically, if you alter with the roughness, for example, if you model this lotus leaf surface and the protrusion in the form of pillars, and you vary the spacing between the pillars, you might see that with large amount of spacing between the pillars, the liquid probably stays in a Wenzel form first. But if they come closer, or rather you make a design where the pillars are closer to each other and the intrinsic contact angle is still like high, for example, 100 degrees, you might have like a hybrid or even a Casey-Baxter state. So you can have a transition between a Wenzel state or a Casey-Baxter state depending upon the intrinsic wettability of the surface and the relative spacing between the roughness features. The bottom line is that more water hitting or hydrophobic a surface, there is a tendency of going to the Cassie-Baxter mode. If highly non-wettable, means hydrophobic pillars are close to each other, they will squeeze the water droplet out. The water droplet prefers to float in the Cassie-Baxter mode. In our laboratory, we use several techniques of altering the surface nature. For example, to impart roughness on a surface, if it's a metal, we use mechanical polishing. We can also use wet chemical etching. For example, if you dip a piece of aluminum or copper on in an acid, that will erode the surface. Basically, depending upon the grain boundaries, the acid will etch away the metal, and that will create micro nanoscale roughness. They are very easy to make. They can be scaled up, means that you have a tiny beaker and you put a small plate inside, you get the etching. At the same time, you have a long, narrow trench, and you have a very long pipe. You want to etch the surface of the pipe, you just dip the pipe in that long, narrow trench containing acid. You can get the similar results. So if you are upscaling the principle to a large industrial application, that can also be easily done. And a chemical etching can be homogeneously deposited or achieved. We do passivation by immersing the metal surface under boiling water, and we use several fluoroalkyl silants to graft on metal surfaces to make them super hydrophobic. These are fairly straightforward methods of rendering a surface hydrophilic or hydrophobic. Now, what we do with playing with these surfaces, I have tried to summarize them in the form of a few tasks. We essentially, in Department of Power Engineering, focus on energy. And as I said, water is intricately related with energy. We also deal with water. So water conservation and energy conservation. Well, energy conservation, I need to tell you one thing, that we often talk about energy conservation. It's kind of a misnomer, because all of us know that energy is conserved. There is no need for someone to really invest research or career in energy conservation. So it's basically the useful form of energy that needs to be conserved. Those who are in engineering and knows thermodynamics, they know that it's called thermodynamic availability or exergy, which needs to be conserved. But that's a different story. Water, yes. The water is also conserved. When we talk about water conservation, it doesn't really mean that we have to store any form of water. Water is it doesn't disintegrate into hydrogen and oxygen easily. So the water is also conserved, but what we really mean about water conservation is how to retain the fraction of potable, drinkable water. The world is rich, or there is abundant amount of water everywhere, but not a very small part of it is really what we can use. And even a smaller fraction of that is what we can drink. So we basically try to conserve exergy and conserve drinkable water through our different treatments of surfaces. So in task 1, I will talk a little about how we can collect or trap fog from some industrial applications. In task 2, I will talk about how we can capture the water that is there in the form of vapor in atmosphere to get drinking water. We can also use the surface treatment to trap water or collect water from solar stills. And we can use this wettability feature to improve the performance of solar photovoltaic cells. So the first thing that I'm going to talk about is cooling tower fog harvesting. And to know that, or to talk about that, first we need to discuss what is a cooling tower. Those with an engineering background, they probably know that a cooling tower is needed for any plants where we want to reject heat in a large amount. For a power plant, for an air conditioning plant, a cooling tower is an integral part. But for others, if you are remembering vaguely even the second law of thermodynamics, it says that when you want to convert heat to electricity or work, you need to run a thermodynamic cycle. And there you cannot use the entire amount of heat. You have to reject a part of that heat. It's the irrefutable second law of thermodynamics. In a power plant, for example, what do? You burn coal or nuclear fuel in a conventional thermal power plant, and then from that you convert it, a part of it, to electricity. The conversion efficiency roughly is around 40%, meaning that a 500 megawatt power plant will actually require, or say a 200 megawatt power plant, which is a 200 megawatt electric output power plant. If it has an efficiency of 40%, it actually burns coal, which produces 500 megawatt of heat, and only 200 megawatt of that comes out in the form of electrical power. The remaining 300 megawatt is released to the atmosphere. How is it released? If the power plant is located next to a big water body like a river, we circulate river water and throw out the warmer river water back to the water body, and we reject that heat. But that's becoming more and more forbidden, because an increase in the river water temperature or temperature of any water body reduces the oxygen level in it and causes a lot of stress to the aquatic life. So what people are doing, the engineers are doing, is that they are building cooling towers. What is cooling tower? Essentially, it relies on the principle of evaporative cooling. On a hot summer day, we all know that if you use a desert cooler, you get to reduce the temperature. Or if, for example, you are on a hot, dry summer day, you are standing under the shower, you raise your hand close to the shower, the water is warmer. You raise your hand, you lower your hand down to the floor level, you find that the water just before the floor is somewhat cooler than the water close to the faucet. Why? Because as the drop is falling through the air, it is evaporating partly, and this evaporation takes the latent heat from the remaining water droplet, thereby cooling it. What happens to the vapor? It is released to the atmosphere, and you get the common picture of cooling out towers spewing large clouds of fog. They are not toxic gases, but they are water vapor which recondensed upon cooling into the atmosphere. So essentially, the cooling towers reject the heat. That 300 megawatt of heat is now rejected to the air. Now, it's not just the heat. What we see here is the large amount of vapor is lost to the atmosphere. The cooling tower plume comprises of three things. One is the vapor. Vapor is colorless. Unevaporated water, which is, as the droplet falls down in a cooling tower, before it cools down, a small part of the droplet which are lighter, they are carried over and they actually go out of the cooling tower. It's like when we speak, we also eject some spits, droplets. It's like the same thing. The droplets, they come out of the cooling tower. These droplets are not evaporated, which means they didn't take part in the heat transfer, or rather the cooling process. So it's a loss of water. Vapor also leads to a loss of water, and the recondensed fog is also a loss of water. How much water is lost? Well, actually a 200 megawatt power plant runs 27,000 meter cube per hour of water through the cooling tower, and 3% of that water is lost. So you can fairly imagine that 3% of this 27,000 meter cube per hour is a very big amount. Per megawatt, it loses almost 1,800 liters per hour. So if you imagine a 100 megawatt power plant, you can fairly easily calculate that it is 1,800 times 100 liter per hour. A colossal amount of water loss. Not only that, this fog also, it damages the electrical equipment in the vicinity. There is health hazard because a foggy environment is not very good for, it leads to respiratory illness. and also the visibility issues are there. So what we actually plan to do is, like, if we could put some metal mesh on this exit plane of the cooling tower cell, as the fog passes through this mesh or the nets, they would actually impinge on the mesh, and a part of this fog will be arrested by the mesh. The challenge there is, if you have an inclined mesh, the droplet should roll down easily and collect on a container underneath the mesh. That way, the fog that is coming out will have some depleted amount of water. A very simple form of metal mesh, a stainless steel metal mesh in a running cooling tower in NTPC Farakka, gave us like 10.5 meter cube per hour of water collection for a 500 megawatt unit. That's a very big amount. We used a small mesh in the size of a badminton racket, but we calculated, from our calculation, we saw that if we could span over the entire cooling tower cell, which was like almost, it's about 10 meter in diameter, means 30 feet in diameter, we can collect this big amount of water. But of course, that is only a small fraction of the water that is passing through it. So there was plenty of opportunity to improve the performance efficiency. And while we try to see what are the avenues of improving the collection efficiency, we actually realized that there are several challenges that we need to first resolve to improve the efficiency. The poor collection efficiency was caused by several factors. For example, we know that it's a mesh which has large pores in between. So there is a large amount of air which bypasses the mesh. The immediate response to this would be, instead of a mesh, just put a solid metal plate. Then there will be no pore, the entire water should be blocked. Even then the answer is no. Anybody who has studied fluid mechanics will tell you that the stream of wind which was carrying the droplets would then see this obstacle in front and they would bypass this metal. So there will be no collection. So you have to kind of fool the airstream as if there is no hindrance. The airstream will come close to the obstacle and suddenly it will find the obstacle where it will have no avenues to bypass this surface, and eventually part of the droplets will impinge on this surface. This is known as aerodynamic efficiency. Now, any droplet which is very close to this mesh, they can also bypass the mesh because the streamlines will pass around the mesh fiber. But because of inertia of the droplet may not be able to negotiate such a meandering path around this. For example, you are running, you and your friend who is a bit flabby are running, and suddenly in front of both of you, there are two electric poles. You just realize, you being very slender, you can steer around and avoid colliding with that electric pole. But if your friend has higher inertia, he cannot negotiate that bend and will eventually ram onto the pole. So the same thing happens to droplets, which has a larger inertia, like larger droplets or droplets with higher velocity will eventually impinge on the fiber of the mesh. The tinier droplets will be able to negotiate this and escape. Liquid which are deposited on the mesh can also be re-entrained because there is continuous flow of air in the fog, in the cooling tower plume. Some of the droplets which are attaching to, or rather attached to the mesh, and they are supposed to drain down along the surface, they may eventually drip prematurely, which means that the droplet will again fall down to the cooling tower, or even after falling down a little bit, the uprising stream may even take it upward, and they may eventually escape through the pores that might lead to a loss. That is called a re-entrainment and premature dripping. And many a times when the liquid droplet is accumulated on the mesh, they may clog the mesh pore. when the mesh pore is clogged, then there is a problem, because suppose the entire span of the mesh, if it is clogged, it behaves like a solid obstacle. And therefore, what happens? Further fog doesn't pass through the mesh. So these are some aerodynamic and surface-related challenges which we found that they are actually detrimental to a high fog collection efficiency. Of course, the fog net has to be sturdy enough. Mechanical failure was another challenge. And therefore, we found that we have to make a mesh that has better aerodynamic efficiency. It has high adhesion so that the droplets are not re-entering. It has a high, easy sliding, very low sliding angle, means it has a high tendency of sliding down to the collector. And then the mesh has to be durable. And a balance of different forces on a liquid droplet on a mesh tells us what sort of wettability do we need to have that kind of feature. And we found that we can either have a hydrophobic mesh or a hydrophilic mesh. And this shows a schematic diagram of the chemical etching that we followed to prepare a hydrophilic mesh by etching in a solution of hydrochloric acid, phosphoric acid, hydrogen peroxide, and FeCl3. It's a stainless steel metal mesh. And after etching and boiling in water, it gives you a super hydrophilic mesh, which when you put some water will give you an image like this. The water quickly is imbibed on the mesh. However, if you after this water boiling and the passivation in citric acid, if you treat it with fluoroalkyl silence or alkaline silent solutions, you can get a hydrophobic or a super hydrophobic mesh. You can see that there is a tiny little droplet on the mesh, which is not wetting the mesh, but it is agile. It keeps jumping from one unit to the other unit of the mesh if you tilt the mesh. The surfaces of the mesh were actually made roughened up by the chemical etching, and then when we coat it with some fluorinated hydrocarbons, then it gives you a hydrophobic nature. And depending upon that, we have like responses. A hydrophilic mesh will give you an arrangement or a configuration like this on the mesh, where a super hydrophilic mesh will actually pump the water along its surfaces in all direction, and a super hydrophobic mesh will have a water droplet which will bead up like this. Depending upon the wettability, we saw that the mesh can give rise to clogging, as shown by this orange region, where the droplet size is small enough so that the droplet is not heavy, as so heavy that by gravity it slides down. The drag is not sufficient to carry it over. But the green region therefore shows a regime where the fog droplet is collected. To decipher this diagram, actually, I can tell you, like, the summary is that if you have a surface where the adhesion is not very high, in a sense that the droplet can quickly, the adhesion along the surface or the lateral adhesion is not very high so that the droplet can slide down the mesh, but the normal adhesion is high so that the droplet is not detached from the surface, because of the, when the air stream passes over the liquid droplet on the mesh, they are not torn away and the liquid cannot escape into the plume. So the surface has to be like that. But at the same time, the surface should not clog up, means that it will clearly, any collected liquid droplet should clearly fall down the mesh. And depending upon those requirements, we found different response by different types of mesh. The collection efficiency as a function of angle over which the mesh will be tilted. And it is observed that a super hydrophilic mesh, in that case, we actually hydrophilize the mesh by not using chemical etching, but by what is known as electro deposition, where we put the mesh in a solution of titanium dioxide, a suspension of titanium dioxide and fast current. And because of this electro deposition, electric field induced deposition, titanium dioxide nanoparticles were deposited on the mesh. That gives rise to the roughness features and the superhydrophilicity, and that surface gave the maximum collection when the mesh was inclined at an angle of 45 degrees approximately. So basically this is still an ongoing work, and we are trying to find out what range of wettability gives us the best collection from a fog which is coming out from a cooling tower. Now, imagine another case, like you are visiting the Sundarbans area where the air is hot and humid. There is plenty of moisture in the air, but there is still drinking water problem. Why? Because the water is saline there. Even the groundwater, if you have a tube well, the water is saline and it's very difficult to drink, survive on that. So how can you ameliorate this problem of water constraint there? If there is a means of collecting the water from the vapor phase from the air, meaning that if you can capture the airborne water vapor. How do you capture? You can condense the water. The problem is that the condensation requires you have to remove the latent heat of evaporation to make the phase change the phase from vapor to liquid. There are other problems also. When a vapor condenses on a surface, it condenses in primarily two different modes. One is called a dropwise condensation, the other is a film-wise condensation. A dropwise condensation is very familiar to us. If you take a can of an aerated beverage, a cold drink, and it's initially just taken out of the freezer and it's a hot and humid day like today, you keep it outside. What do you find? You find that initially the surface of this, the metal surface of the container, water droplets beat up on the surfaces. This is called dropwise condensation, when the condensate forms tiny little drops on the condensate surface. But soon what happens is that, during this condensation, what happens is the droplets grow, and as they grow to a large enough size, the gravity pulls it down. When they are pulled down, the initial droplet is disappearing, and also as it rolls down through the surface, there is sweeping by the droplet. So this entire section becomes stripped of the new droplets, as if you scrape the surface, and on that region, again, tiny little droplets start to regrow. The cycle continues. But unfortunately, what we find later on is that the droplets on the surface, they eventually are not dislodged so easily, and what they do is they coalesce on the surface, and eventually they form, after coalescence, a large film. Sometimes you see channels with intervening areas where you still have dropwise condensation. The type of condensation on the left is known as dropwise condensation, while on the right you see a film-wise condensation. And it is seen that the heat transfer rate in the dropwise condensation is usually 1 order of magnitude higher. Why? Because of two plain reasons. One is that for condensation, you actually, and this is a typical picture of condensing surfaces, like you have a superhydrophilic surface. There you see typically film-wise condensation. The images on the right-hand side, this colored image actually corresponds to an infrared imaging or IR image of this condensing surface, where you see the channels of water and the film that is formed on the surface. This is showing dropwise condensation on a superhydrophobic surface, and a mirror finish aluminum surface. It also shows partly dropwise condensation, and towards the bottom of this surface, you see accumulation of the liquid, which is forming a puddle. out of these things, these types of condensation, the dropwise and film-wise condensation, we see that the dropwise condensation has a better condensation rate. Why? Because in a dropwise condensation, the nucleation of vapor takes place on the solid boundary instead of the liquid surface. And the nucleation density on a solid, which is known as a heterogeneous nucleation, is much, much higher than homogeneous nucleation. What happens in case of a film condensation? Like in this case, any fresh vapor on the vapor side will eventually nucleate on the water surface. If we go back to the first image, vapor is here, and any vapor that needs to condense in case of film-wise condensation will have to condense on the liquid surface. And this is known as homogeneous condensation, which has a much lower nucleation rate than the nucleation rate that you see in case of heterogeneous media, like on a metal surface. So number one is that this film, on the film, the nucleation density or the nucleation rate are small. Secondly, you can clearly see that the presence of this liquid layer actually adds to a thermal resistance. Whereas in this case, yes, these droplets also add to thermal resistance. But I mean, these droplets, if they are shaded, I mean, if the droplet grows and eventually it's shed, when its size reaches a certain value, then a new smaller droplet grows again at that spot, which means that the average size of the droplet on a particular domain, it doesn't grow up to a very large value, which means that the resistance offered by the liquid is not so large. So that gives rise to a better condensation rate when you have a dropwise condensation. So nucleation barrier is smaller for heterogeneous surface. That is what gives you a higher condensation. And the liquid film offers a thermal resistance to the overall condensation. For these two reasons, we want dropwise condensation. And even when the dropwise condensation is done, we want the droplet to be shed at a faster rate. But why don't we see dropwise condensation on a sustained manner? Well, in a real surface, when we see that the nucleation is occurring, it leads to tiny little tiny little drops to form. But as the time passes, these neighboring drops, they do not move, but they coalesce. And as they coalesce, if the contact angle hysteresis is large enough, they are held back on the surface. Even if the surface is vertically held, the liquid does not shed because this contact angle hysteresis holds it back into its place. And in that case, what happens is that these coalesced droplets will form a film, and that will lead to a film-wise condensation. So in a realistic surface, film-wise condensation is the final sustainable mode of condensation. Dropwise condensation soon, because of some practical difficulty, it transitions into film-wise condensation. So what can we do to prevent this film formation and sustain the dropwise condensation? Well, we have to make the surface such that it doesn't form the film. Also, we have to make the surface so that the droplet is shed very easily. Because as I mentioned that even the droplet sitting on the surface in dropwise condensation has a thermal resistance associated with it. And whenever it has a thermal resistance, higher the droplet size, larger is the thermal resistance offered by the droplet. There are other thermal resistances like the gas phase boundary layer resistance, and there is an interfacial resistance offered on the droplet surface, which also needs to be overcome for a better heat transfer. Better is the heat transfer or the heat release, then higher is the condensation rate. It is seen that if the droplet, which grows over time, it grows in size, what happens is that the resistance offered by the liquid increases. So what do we need to do? In order to improve the condensation rate, we have to minimize the growth of these droplets. So that what is the requirement then? We have a surface. As the droplet size, the moment the droplet size, because of condensation, it grows beyond a certain value, we have to remove it from the surface. So early shedding is very important. How to shed the droplets young? We can make them the surface low hysteretic. How do we make it low hysteretic? Well, some superhydrophobic surfaces have low hysteresis, like lotus leaf. But here we cannot have a lotus leaf for heat transfer because the base of the lotus leaf has a very poor thermal conductivity. So maybe we need a highly thermally conducting base. So maybe on a metal surface, we need a superhydrophobic nature. So a superhydrophobic metal surface can give you some sort of self-drying behavior, like this aluminum surface, which had been coated with fluoroalkyl silane. You can clearly see it's not held vertically, it's actually held at a very small inclination angle, and you can see that water dispensed on this metal rolls down very easily. So we still have a conflicting feature on the surface. I just mentioned that in order to shed the droplet early, we need to basically, we have to essentially, what do we need? We need to shed it. We need to shed it early. When we need to shed it early, we actually have to make the surface superhydrophobic. But when we are making it superhydrophobic, that means the material itself hates water. The nucleation barrier to the surface is very high. Higher is the nucleation barrier, lower is the nucleation rate, which means on a highly superhydrophobic surface, the vapor is reluctant to nucleate, which means the nucleation rate and the growth of droplet will be hampered. But if we make the surface hydrophilic, then droplet shedding becomes an issue because a hydrophilic surface has a very high contact angle hysteresis. So this is a challenge. We have conflicts. We cannot make the surface totally superhydrophobic. We cannot make the surface hydrophilic. What to do? There are several techniques that people are trying out. For example, if we use gravity to do droplet shedding by mechanical shaking, or there are other features where they leverage droplet jumping on a highly superhydrophobic surface, or electrostatic mechanism to remove droplets from a surface. All these mechanisms require investment of additional energy, but what we rather prefer to do is known as a biphilic approach. We have talked about hydrophilic, hydrophobic. A biphilic means that we have a surface which is superhydrophilic or hydrophilic at one part of the surface and hydrophobic on the other part. What you see on your left is a surface that has a superhydrophobic background. So any water droplet on it will form beads like this, contact angle above 160 degree. And interspaced within this, there are strips like a zebra crossing, hydrophilic or superhydrophilic strips. Any droplet on this superhydrophilic regime will be spreading on this surface, just like a homogeneous surface spreads water, which is dispensed on the surface. If any liquid is dispensed on the borderline, this is what will happen. On your left, you have this greenish patch, and on your right, you have this hydrophilic. So the greenish patch is superhydrophilic, the red one is superhydrophobic. And then let's see what happens to a liquid droplet which is dispensed at the border. So what happens is that on the hydrophobic side, the droplet falls, and as the droplet touches the hydrophilic side, it experiences a movement. This movement is caused on a horizontal surface, so no other external force acts here. It's only the surface energy which drives the flow. So it's a capillarity driven flow, with no additional energy input. Can we leverage that in improving the condensation characteristics? That was our idea. So we actually then went into creating a biphilic surface. Biphilic means surface on which two extreme contrast of wettabilities are present. So on a metal plate, we used selective etching, meaning that the aluminum plate, which was initially covered with a covering plastic layer, we removed part of the plastic layer by laser etching that, and then dipped it in chemical, in acid, and boiling it in water. We get these strips as superhydrophilic, whereas the remainder of the metal, after removing this sticker, it remains as a mirror finish aluminum surface. The roughness features are created by chemical etching, whereas a grafting of fluoroalkyl silane is found not to basically alter the surface roughness, but create a feature, or rather a hydrophobic environment on the top. And what we find there is that when we have a surface which had a superhydrophobic nature, and interspaced on that you have superhydrophilic tracks. I will play the video again. This 800 and 1000 denotes the spacing between the two tracks in the vicinity. We find that the region which is between the two superhydrophilic tracks, so they have much smaller size of average droplet diameter than this region. So what we claim here is that the average size of the droplet on the hydrophobic region is less when we have a strips of superhydrophilic patterns in here. So depending upon the spacing between the superhydrophilic strips, we have different extents of droplet diameters. So what happens in this design is that any droplet which grows in between the two hydrophilic regions, they cannot really grow beyond this width of this section, because they would eventually touch any one side of these strips, and they would eventually get pumped in the downstream direction. So that gives us a reduced average diameter of the droplets, and that means what? The dropwise condensation heat transfer is faster because the droplets have a lower thermal resistance. We saw that with the increasing spacing, the droplet size increased, which means a finer spacing between the comb-like structure, you have a smaller droplet size, and it should give you a better condensation. But at the same time, we found that whenever the condensation occurs, the hydrophilic channels, they get filled up with water. Any droplet that is formed on this hydrophilic, or rather the mirror finish part of the metal, will eventually drain onto the superhydrophilic part. And this draining actually works very fine when the condensation rate is small, but if under highly wet condition, these drains get clogged. Somewhat similar to the roads of Calcutta. When it rains very small, the road remains dry because the drains on either side, they are taking away basically they are draining away the water. But if it rains very heavily, then the road gets waterlogged, which means that you have to put a pump in the drains to even take care of this larger supply of influx of water. So we needed a pump in these strips to eventually withstand a higher condensation rate. And we cannot really have so many number of pumps on this surface. Then we have to rely on the capillary or the surface tension force. Generally, if you put a liquid on a surface, and if the surface is superhydrophilic, what you will see is that the liquid immediately spreads on the surface. And this spreading is taking place by two means. One is known as Hemi Wicking, where you put you put a drop of water, and through the crevices of the superhydrophilic surfaces, the water meanders everywhere. On the other hand, if the surface is superhydrophobic and you deposit a liquid which makes a curved interface between the liquid and the gas, it creates this curvature, and the surface tension creates what is known as Laplace pressure driven pumping or capillary pumping. So this capillary pumping arises because of the curvature of this surface, and the Hemi Wicking occurs because of the intrinsic wettability of the surface. We can use both to move liquid from the surface when it's condensing heavily. How fast we can move? Because this Hemi Wicking, we already know that if we put a drop of water in a blotting paper, it is the Hemi Wicking or the wicking that leads to the transport. But there is a limit to this transport rate, which is known as Washburn limit. In fact, it's the same limit that leads to capillary spreading. I'm sorry, my PowerPoint just crashed. Wait a little, and I'll again pull up the presentation.
Maybe somehow it got closed. Maybe.
Sorry?
Somehow it got closed, your PowerPoint.
Yeah, it showed that it crashed. So
okay.
I think it was because of a movie. So let me, I've opened it and I'll go to the sharing mode again.
Okay.
And just so I hope you can see the corresponding
yes.
slide now. Yeah.
Yes.
So this wicking, Hemi wicking, is something we have to basically we have to shoot past this Washburn limit, or rather exceed this Washburn limit. And how can we do that? That was our thought. So, and also we needed to push or overshoot this limit without spending any extra energy. So what we did was we tried to develop surfaces which had wettability patterns. What you see on this plate is it's an aluminum plate, and the whitish part of that was rendered super hydrophobic by imparting roughness. It had some titanium dioxide coating, but that material doesn't matter. We can even use other methods of making it super hydrophobic. And some internal part, you can see these triangular channels which we made super hydrophilic. So they are loving water. The whitish part is hating water, and that's why you can see, like a lotus leaf, the droplets are in a bead-like appearance. And when we put a gentle tap on the side of this plate, they disappear. And when we see it under a high-speed image, we see that what actually happens. The droplets, the plate is moving from right to left. Because of inertia, the droplets move from left to right. They don't move, they stay the same. And eventually, they fall on those super hydrophilic tracks. And as you see on the super hydrophilic tracks, the liquid is pumped from the narrow side to the wider side. I'll repeat this, playing this video. So none of these droplets actually escape the capture, and they eventually, you can see the bulges, they are pumped from the end of the camera away from it. This is a horizontal plate. It's not inclined in this direction. So there is definitely a pumping which happens because from the narrower edge to the wider end. And this is actually caused by Laplace pressure driven flow. To explain that phenomena, we found that in an old Nature article, people have found that when you have striated patterns or strips of superhydrophilic surfaces in a superhydrophobic background, and you infuse water in those lines, they eventually form bulges. The water, additional water, it doesn't widen the entire channel, but it forms local bulges because of some instability. They can even coalesce the adjacent bulges may even coalesce. Our simulation with Surface Evolver also a software that also showed formation of some bulges like that. So a liquid on a superhydrophilic track, which are juxtaposed between two superhydrophobic domains, will give you a bulging structure. And this bulging structure is what we found when the droplet touched the superhydrophilic strips. And whenever we have such a bulge on a diverging channel, we find that the force occurring at the interface of the solid and the liquid, they are directed this way. And if you look carefully, the force are occurring at the points where the liquid actually touches the solid surface. And the direction of these arrows are actually, they follow the direction of the meniscus. And depending upon this force, you get a net unbalanced force on the entire liquid meniscus in the forward direction from the narrower side to the wider side. There's an easier explanation to that, which says that the curvature of the liquid on this narrower side is more than the curvature on the wider side. And whenever we have a curved liquid, there is a Laplace pressure which is developed, which is expressed as the surface tension divided by the curvature. So the smaller is the droplet's surface tension divided by the radius of curvature. Smaller is the radius of curvature, meaning larger is the curvature, higher is the Laplace pressure within a droplet, which means a smaller droplet has a higher pressure than the ambient inside it, which also means that the liquid which has a higher curvature, a smaller radius of curvature in this upstream region, has a higher Laplace pressure than the downstream. So there is a net pressure gradient in the forward direction which propels the liquid droplet. It was experimentally even verified that we had a gradually opening channel, and whenever we deposited it on a horizontal surface, it moved forward. But if we tilted this surface back, it was held stationary, which was balancing the gravity, which means the capillary and the gravity force exactly balanced. And by that, we were able to even measure this capillary force, and the acceleration due to this capillary force was calculated, and it matched to the observed acceleration of the liquid droplet on a horizontal surface vis-a-vis the force generated on a backward tilted surface. With this, what we found was that the liquid droplet on a horizontal surface, basically, when it moved from the left to right on a gradually opening channel, we were able to exceed or surpass the Washburn limit. Here, the velocities are plotted, and what we see as a dotted line as the Washburn limit, and the actual velocity was much above the Washburn limit as the liquid front progressed in the direction of the channel. So basically, it led to capillary Hemi Wicking and the Laplace pressure-driven flow together, and that leads to a faster, more rapid transport. I will skip this slide, but actually there are three regimes of capillary transport or motion that we observed, where initially the liquid was pushing or transporting through the pure Washburn type for a very small period of time, but then soon the capillary force overtook, and finally towards the end of the movement, it was the viscous dissipation that eventually retarded the force. But in this linear regime or region, that's when the liquid transport much faster than the Washburn limit, which we observed. Now, how does it help? Well, it helps us to transport the liquid on the condenser surface. Now, imagine we have a network of such tracks where we have a surface where the droplets grow, and as they touch the superhydrophilic tracks, they are pumped by the Laplace or capillary force so that the liquid is pumped and then eventually drained. An array of these triangular shapes in the form of like a banana leaf was created. Again, it was nature inspired, and we found that Any liquid dispensed on this type of patterned surface actually led to a pumping of the liquid droplet from the narrower end to the wider end. We we did improvement in design where the spikes were staggered, where if we put two droplets from either side, the pumping may be affected because two streets emptying on the same drain may eventually clog the drain. But if these are staggered, then the pumping was even finer or faster. And a surface, condenser surface, which had this type of design gave rise to condensation pattern like what you see here. This is a mirror finish surface where we have etched super hydrophilic tracks. These tracks you see from the narrow end to the wider end, they drain the water and they pump it to a highway or a larger drain where they are dripping down at the bottom. Now, what is important in this surface? Unlike the surface of your cold drink container, no matter how long you leave this surface condensing like this, it is not going to form a film on the top. Why? Because these droplets, you look very carefully, they cannot grow larger over time because the droplets, you look here, a droplet, I'm looping this, but you see that a droplet will form here, and as it grows and touches this wedge, it drains down. So on an entire surface, we have several such superhydrophilic drains which regularly removes the liquid, the droplets, and fresh droplets grow on the surface. Fresh droplet means they have smaller size, and we just saw that smaller size droplets offer lower thermal resistance, means higher condensation rate. Sounds intricate, but we see very clearly that there is no film covering the entire surface. Moreover, the liquid drips down at regular intervals from intended spots. And what is obviously most important is that it led to 30% increase in heat flux and 35% improvement in heat transfer coefficient. So imagine the condenser in a power plant where you reject 300 megawatt of heat transfer. If there is a 30% improvement in heat flux, you can make the surface 30% smaller. So that is a better engineering design. A 30% improvement in heat flux means 30% heat rejection, or recalescence means rejection of the latent heat, means you get a 30% improvement in water collection from the atmosphere. Actually, there are some other engineering applications of this which are relevant in air conditioning industry. We all know that our air conditioner, which the indoor unit of the air conditioner has several tiny little fins if you open the indoor unit of the air conditioner. Any liquid that condenses, because our indoor air has humidity and the air conditioner surface is cooled, because of condensation, liquids form between the tiny little fins, and eventually the liquid droplets clog the fins, which reduces the performance of the air conditioner. There is a water line which drips the water, but that is not sufficient. If the metal plates can drain the water on their own with a design like this, you always can improve the performance of the household air conditioner or even industrial air conditioner by this much amount, which saves energy, which saves natural resources. The third task is we use the same wettability engineering in solar steels. Solar steel is a very old technology. Like you have murky water, and you by virtue of, or by means of distillation, you can use solar heat to evaporate the water from this murky or dirty water and condense the vapor on a colder surface and collect the water. Again, what happens here is that in a common solar steel, there is a glass surface which acts as the transmitter as also as the collector. A common problem in a solar steel is that any evaporation that takes place here and any condensation on the glass top leads to collection, but many a times the droplet which forms on the glass surface drips back into the murky water pool. That defies the purpose of the collection. So what we need in a good solar steel is that the vapor would come out from the pool of dirty water, and then it will condense on the glass surface, and it will not detach immediately, but it will gradually slide down to the collector at one end. How can we do that? Easy sliding is rendered by making the surface super hydrophobic, but we know that a super hydrophobic surface always acts as an inhibitor to condensation or nucleation. So there is again an optimum criterion for which we have to make a surface optimally wet. We used the several techniques to coat the glass surface, and we made it hydrophobic, like this one where we found very small droplets on the underside of the glass cover. We made the surface super hydrophilic, where there was no film, no droplets. There was a continuous film, and we had a natural or a regular glass plate where we had a mixture of drop-wise and film-wise condensation. And we find that a hydrophilic glass was, as a matter of surprise, gave a better collection than a hydrophobic or an untreated glass. So we were able to improve the water collection by treating the underside of the glass cover, and the water collection improved by a large amount. So did the heat transfer coefficient. So the bottom line here is that by changing the wettability of the glass cover on the underside of a solar steel, we were able to improve the water collection. Now another application of this wettability engineering we found in solar photovoltaic cells. We know that the solar photovoltaic cells are emerging as the most dependable option for renewable energy, because its maintenance free means that there is no moving component. You fabricate the solar cell, you install them, and then you run them. There is no rotating device. You don't have to pump things, etc. But there is a problem that dust is always a pestering issue, and the coating of dust, particularly in a country like ours, always gives rise to a gradual reduction in the solar photovoltaic cell performance. And most of these areas which are abundant in sunshine, they are deprived in abundant supply of water. Manual cleaning of these solar cells using a lot of water is a very wasteful situation, because then it requires regular human intervention and lot of water, which is not good. So our idea was that, can we develop a surface which would be transparent to the solar cell, solar radiation, and also it gives rise to self-cleaning feature. With very small amount of water, it will remove the dirt. What is a self-cleaning surface? Well, in an ordinary surface, suppose these are the darts, you put some drop of water, what will happen is that the water will stick to the surface. Sometimes the water may pass, but the dirt will stick to the surface. Sometimes the water and the dirt will stick to the surface, the water will evaporate, and the dirt will stay there. That is what we find often on our windshield of the cars, where the dirt and then the rain eventually gives rise to ugly looking marks on the windshield, which we have to clean. But imagine we have a surface which is in a Cassie-Baxter state. The dirt stays there, and any droplet of liquid that falls on the surface will roll down the surface, pick up the dust, and eventually roll off, cleansing the surface. That is what we intend to manufacture. Now, this is a hydrophobic surface. Now, a hydrophobic surface or a super hydrophobic surface requires two things. One, the surface has to be low energy, means there has to be a chemical which will make it water repellent, and also to make it super hydrophobic, we have to make the surface rough. And there is a conflicting feature, because we know that solar radiation comes through this surface, and if the surface is rough, then it leads to scattering. And the scattering increases if the roughness features are more, and that leads to a reduction in the solar radiation transmission, or there is a higher attenuation. So we have to strike a balance between the losing the transmissivity as well as better self-cleaning. What we did was we took a glass surface, which is silica, and we tried to bond silica nanoparticles on the surface. Bonding silica on a silica glass requires a silica intervention. So we used a silicic acid, and silicic acid requires an in situ preparation. So basically we use some tetraethoxysilane, which is a silicon containing chemical in an acidic environment, and we formed silicic acid. And in a silicic acid, we basically sprinkled an ethanolic solution of silica nanoparticle to create a sol gel in which we dipped the glass. As we took out the glass from this sol gel, the tiny little nanoparticles were bonded to the glass surface through hydrogen bonding, because the glass has silica, the nanoparticles has silica, and this silicic acid has complementary silica, the complementary wings, and through hydrogen bonding, the silica particle and the glass substrate bond. And when we bake this surface, the bond actually, the hydrogen bonding becomes a covalent bonding, and these tiny little glass aggregates form rough structure on the glass surface. And then we coat on it a fluoroalkyl silane. So it's pure chemistry. We basically have a chemist, or rather we have a faculty from chemistry department as a collaborator, and we form a collaborator which is also known to JBNSTS, is Debojyoti Ghoshal, so Moitri knows him. And we form a silane coating on this rough surface, and we make the surface water repellent. This is the chemical structure, and that is how the glass surface looks. Now, there is clearly some loss of attenuation, and you can see these structures on a dark background, which means light will be attenuated a little bit. This is the structure of the nanoparticles, not the nanoparticles, the clusters under a microscope, and the AFM, the atomic force microscopy, gives us the roughness data. We found that when we passed simple sunlight through this surface, without a coating, you get like this white open squares at the without coating surface, and upon coating, there is a small reduction in the irradiance as it passes through the solar photovoltaic cell. So we just used the glass, and we measured the irradiance that passed through the coated glass, and there is a percentage attenuation which hovered around 8%. To our surprise, we found that the attenuation in voltage of the solar photovoltaic cell was even smaller, to the tune of 4%, because the attenuation of visible light and the IR lights were different, and the solar photovoltaic cells had a composite component of the IR radiation also to its generated power. So the idea was, like, if we see that there is not much loss of attenuation using this coated surface, the immediate question was how well it cleans. Now, to see that, first we see how an impact of a water droplet on an untreated clean glass surface will look like. We had a glass surface inclined at 45 degrees, and we deposited water droplet on it from a height. And what we saw, we used like a 5 microliter droplet from a height of around 25 centimeter. And as the droplet impacts on a glass surface, because of the hydrophilic nature of the glass slide, it spreads heavily, but then it doesn't go anywhere. It sticks to the surface. You can see that it's sloshing right from here to here. The entire surface is wetted by glass, and then it evaporates slowly. Any dirt in this region will be trapped here at the bottom corner of this water pool, which will eventually stay there. Not very good. How does the coated surface look? Well, let me show. I'm sorry. So a droplet on the coated surface will again spread like this, but unlike staying there, it's hydrophobic and it will eventually be dislodged. It will jump from the surface. which means that it will clean the entire surface in this range and will leave the surface with the dart, because the darts will have a higher affinity to water. This is what happens when you have a dirty surface. You can clearly see the darts there, and as the droplet moves away, it removes all the dart that was there on the glass surface. Upon impact, it spreads over a wide range, which means it cleans a wider region. And as a result, what we find here is that, so this is what happens again when we have this dusty surface. It moves away from the surface, and what we get here is that when we have a treated surface, we compared how well the performance degrades, or rather how does the performance degrades over time when we have dust deposition on a glass surface. So what we see here is that if we deposit different levels of dust, which means over time the dust loading increases, how does the voltage of the solar photovoltaic cell goes down? If we have an untreated surface, which is this greenish tinged box, it goes down as the dust loading increases. The treated surface, that also, if the dust loading increases, the voltage goes down. And you can clearly see that the voltage of the treated surface is slightly lower than the voltage produced under the untreated surface, voltage produced by the solar photovoltaic cell when it is covered by the untreated surface, because untreated glass has the better transmissivity. And with the deposition of dust, both the treated and untreated glasses, they see a decline in the solar photovoltaic cell voltage output. But what happens when we have a measured quantity of water deposited on the glass surface, 15 drops or 20 drops? I take this 20 drop scenario, 20 droplets of water was sprinkled on the glass slides. If the glass slide is treated, means untreated, then or on a regular glass slide, depositing 20 drops of water, it improves or it cleans the glass surface to some extent. So that's why the voltage is regained to this extent. But if the surface is treated, T stands for treated, then there is further improvement in voltage output. You see, with the larger dust loading, the difference between the recovered voltage from an untreated and a treated surface, it improves, which means, yes, you are losing a very small amount of voltage if you are offering a treated glass surface, but at the same time, it gives you much better performance regain whenever you use a measured quantity of water to clean the surface. So under tight water budget and periodic automated cleaning, say you can use a sprinkler which opens, say, once in a day and sprays a very finely divided droplets spray on the surface, you can clean the entire surface with very small amount of water and regain the performance. You were able to gain the performance almost back to the normal level. So this percentage recovery improvement clearly shows that there is a chance or a promise of treating the surface better to improve the energy output. Now, talking about the energy, we saw energy and water can be like these fields of energy and water can benefit from this surface engineering. But in today's time, we also have a high demand on any engineering application to benefit the healthcare, particularly in the face of this COVID outbreak. And there, a lab on a chip device is often heard as a useful tool. Just to give you an idea, lab on a chip device means you have a very small microfluidic device which can fit on a handheld powered device like a credit card size chip on a handheld device, and that can be used for detection or diagnosis of several things like pathogen, or it can be used for water quality monitoring, for forensic detection, drug development, so on and so forth. But what essentially this microfluidic device will have is a small microfluidic chip which has very narrow channels of several hundred microns in diameter, and it consumes very small amount of reagent, but it has a feature which is like it can uptake liquid samples that you want to treat. For example, in case of COVID, you take the sample, the saliva sample, and you treat it, and you do some specific reaction, and there is a sensor which detects the presence of a particular pathogen in a sample. It can be applied, or this is a very generic design and applies to any sort of biosensor. The advantage of a microfluidic chip is the tiny volume that is required. So it's a lab on a chip, means in a chemistry laboratory, you do the chemical reactions in large beakers. There you need a large amount of sample and a large amount of reagents. But if you are performing the same reactions in a very small channel, then the reaction time is reduced, the reagent consumption is reduced, the cost is reduced, and more importantly, instead of one lab, you can have multiplexing, meaning hundreds of such labs working simultaneously to improve the speed of detection, which is very important even in today's context. A typical device, a lab on a chip, it's also called a point-of-care diagnostic device, where you can send this device to the region where it's needed, means point of care, and you can mass deploy it if it's cheap and have the beneficial effect. So in today's context, if you can have a point-of-care device which is sent out to every corner, every locality, where the health worker can do the diagnosis on a doorstep, from doorstep to doorstep, that's the best scenario you can have. Now, to do that, you need a device which is inexpensive, but yet which is accurate. And these rapid diagnostic tests are there for a while, and they are being used for several different purposes, ranging from, say, pregnancy detection to veterinary and other biomedicine, even for blood sugar monitoring. Also, these test kits are available. Only thing is that to expand the same thing for the COVID detection. And probably I'm not an expert in this field, so whatever I am showing you, it's borrowed from the literature pool, and I'm not going to really expand much on that, because Moitridi already mentioned that you have had several lectures on this. So basically, the idea here is to for a detection of the COVID is to identify the presence of any surface features or surface proteins in the sample. Basically, there are several techniques, like you can have, right now the PCR testing, what it does is that it basically detects the nucleic acid after multiplying the nucleic acid to the desired concentration level. But and in a more direct detection, a faster detection is possible if we are able to detect the presence of the surface proteins, like any of the S, E, M, or the N proteins. Out of the several detection techniques, one area where we find that the surface-driven or these microfluidic devices can have a penetration is the indirect test or the serological test, where we can detect the presence of antibody in blood sample. In today's newspaper, you might have seen that initial testing of the serology testing in Delhi has shown that almost 23% of the samples have shown the presence of antibody, which means that maybe there is a large level where the patients are asymptomatic, or they have developed some sort of immunity or like antibody against the virus. Knowledge of that is very important, because the economy has to open, or rather the society has to open, and before that we need to know what fraction of the population is already immune to the disease. Sensitivity and specificities are very important in such devices, and I'm not going to elaborate on that. Probably you already know what these sensitivity and specificities are. Are they, Moitridi? I mean, have the previous lectures dwelt on those things? Well, if not, I mean, the sensitivity is basically, it's how many, if you test, for example, 100 samples, and you a 90% sensitivity means that out of these 100 samples, suppose you diagnose 90% of them without fail. There is the failure rate should not be like more than that. So 90% should be true positive in the sample, and 10% it also means that 10% is false negative. False negative means it also detects 10% as the positive case where actually there is the patient is not infected. Specificity means that if there is a test, there should be like 90% should be true negative. Means if we are testing a wide variety of samples, and like if 100 patients are there, out of which all are supposedly they are negative, the detection should give you 90% as true negative. Means it should tell you that 90% of the patients are negative. By mistake, it reads 10% of them as false positive. A true sensor should have 90% sensitivity and specificity. Of course, it depends whether you are doing a screening or a regular detection, but that's what the benchmark should be. So a serology test, what does it basically based on? Serology means it tests the blood sample, and we know that, or if we do not know that, and it's just a piece of information that we should keep in mind, is that whenever a patient is infected, and these are you see the graphs, it's the days after the symptoms appear, the levels of antibodies, and there are two types of antibody levels which peaks in a patient. The IgM and the IgG, they peak as the patient is infected. This is the duration when the patient has fever. And post-fever, the IgM and the IgG level increases. IgM tapers off very fast, IgG takes longer. The idea is that if we can have a patient or any person do a serology test, if somebody is found to have an IgG or an IgM, we know that the patient had either fever, or even if the patient may be asymptomatic, has developed the antibody. So it's a detection post the infection. If you see the negative in both IgG and IgM, you know that the patient may not have contracted the disease. So the detection principle is basically called immunoassay. Immunoassay means basically we are leveraging the immunochemistry between the antigen which are present on the surface of the virus and the antibody that the patient develops in the blood. The principle of this immunoassay, they are also called lateral flow immunoassay, is something like this. In a blood sample, which is ideally like, I mean, if the patient had already COVID, it will have IgM and IgG antibody. So in the blood sample, we deposit the blood sample on the microfluidic chip. And inside the microfluidic chip, there will be a micro reservoir of some pre-suffused layer of antigen. So the COVID-19 antigens will be pre-suffused here. So to develop such a kit, you have to have the COVID-19 antigen precisely ready. Now, of course, there are several coronaviruses, and you have to correctly identify the right COVID-19 antigen and tether to it some markers. In this case, gold nanoparticles are used for the tethering markers. As the liquid flows through this sample pad into the conjugate pad, because of the immunochemical reaction, the antibody binds onto the antigen, COVID-19 antigen. If the antibody is not present in the blood sample, there is no question of binding of the antibody to the antigen. Now, the antigen-antibody conjugate is now then allowed to flow over a porous membrane, and in that membrane there are 3 lines, and these lines are actually pre-grafted with another layer of antibody. They are called anti-human antibodies. So this line has anti-human IgM antibody, and this line has anti-human IgG antibody, meaning that this anti-human IgM antibody has a propensity or affinity towards IgM antibody, and this anti-human IgG has an affinity towards the IgG antibody, which means that if the sample had these antibodies present and they already have combined with the nanoparticle functionalized antigen and now pass over these lines, the other ends of the antibodies will tether to this anti-human antibodies. If they are present, then that will mean that the gold nanoparticle tagged antigen plus the antibody is bound onto the surface. If the antibody is not present, these nanoparticles will simply elute away because the nanoparticles are bound to this anti-human antibody only through the IgM or IgG antibody things. So that means we are able to attach or accumulate the gold nanoparticles only if on the M, we will be able to accumulate the gold nanoparticles on the IgM or M line if there is IgM present in the sample, on the G line if IgG is present in the sample. If this is not present, what do? Well, we still need to check whether these lines did not show the gold nanoparticles, whether because there was no antibody in the sample or whether there was not sufficient capillary flow. To ensure that there was sufficient capillary flow, we have a third detection or control line which actually catches any of these gold nanoparticle plus there is a human, this rabbit, it's a general, it's called the gold rabbit IgG conjugate, which no matter whether the target antibody is present in the blood sample or not, is eventually captured on the control line. As these nanoparticles are captured in the control line, a large number of nanoparticles, when they are captured, they form a visible line on these things. So if you have a strip where you drop the blood sample, this shows the protocol. You drop a blood sample taken through a lancet, and then you put a buffer, a washing fluid, so that the sample flows through this surface through a capillary action. I'll tell what this capillary action is, and then it elutes over the surface and leads to this reaction. If IgM is present in the sample, then the IgM line will show a dark line. If IgG is present, G will show a dark line. If nothing is present, there will be no line, only the control line will show a dark line. But in case of positivity, all the 3 lines will show a dark line. So this is a case where you have an IgM positive, this is an IgG positive, and this is an IgM IgG positive, which means that you are either in this phase when you are only IgM, which means you are just in the phase of contraction. If you are already past in this, only IgG is present, that means you have had this fever and it's subsided. And if you have both, then you are in this regime. So this is a typical serological test that is done. Now, this is the building block, but the question is, how do the flow take place? There is capillary flow in it. What sort of capillary flow? Washburn type of flow rate. What are the tasks of these microfluidic chips? We need, for a better detection, we need faster transport. We also need multiplexing. For example, this one is only one line. We put a drop of blood in one line, it goes. Suppose we have a multiplexing, means we put a drop and there are several channels. We have 5 lines. There are 2 possibilities. One is that you have 5 lines and in 5 of them you do a repeat test, meaning that you, by some mistake, maybe the capillary flow has not taken place in one sample, you don't have to wait for 10 minutes. You actually do a multiplexing. So in 3 out of the 5, you get a result. You can claim or publish that result, or rather rewrite it in the report. Or there can be several other things, like it is not, I mean, it's not always possible to know whether there is a fever and the fever is because of COVID or some other illness. And if you, in a single device, put these in the conjugation pair and on these lines, other complementary antibodies to detect other diseases, then one simple pair or one simple kit can serve as a detection tool for 3 or 4 possible competing diseases. That actually is more effective, because it's not just that you treat or diagnose a patient whether he has a COVID or not. You need to also diagnose what if it's not COVID, then what. So multiplexing is one very important tool that we need to build up on these microfluidic devices. You have to have a liquid metering on the chip, because you want to control how much liquid you want to push in that device, and merging and mixing, because that's a very common protocol in any chemical lab. You have to mix the reagents for the reactions to occur. And that's where we are leveraging the capillary driven flow. We already talked about how we use these diverging tracks to move liquids on the surface at a faster rate. And now we try to implement them on chips. So this is, suppose, a platform where you dispense 2 liquids, maybe a blood sample and maybe a thinner. It's not exactly, it could be the buffer and the blood sample, and you want to basically mix them in a perfectly metered fashion. We used, on a hydrophobic background, 2 hydrophilic tracks and dispensed on them these liquid samples. The design is such that on a horizontal surface, the capillary force created the pumping, led to a mixing, and eventually dispensed it down there. This dispensing unit can have the input for the rapid detection kit that we mentioned, where the blood sample was dispensed. This is highly repeatable, and this is what happens when you see it under a high-speed camera. This is how the coalescence and pumping takes place. You can have several different substrate, like this is on a paper substrate, and you can have like this mixing and merging and metered dispensing. This is how we can quantify the mixing on this type of surface. The 2 liquids that were dispensed and merged, they were actually mixed also, and this is showing how well they are mixed. We have dispensed 2 liquids, and they are actually ammonium thiocyanate and ferric chloride solution, which gives rise, upon mixing, a dark chemical and ferric thiocyanate. So the darkness of the liquid tells us how well they are mixed. And it tells us that, yes, the liquids are mixed in a very small period of time. You see this time, it's in 350, less than 350 milliseconds when we have the mixing. And the mixing can be enhanced by providing tracks of superhydrophobic patches on the same surface. And then this liquid can be further used for detection. I'll skip this, but talking about the multiplexing, we can use the tracks to split the liquid that we drop on the surface and have it pass on multiple channels. So each of these end track can feed to one of those lateral immunoassays. So one single drop of blood can be split into 5 aliquots or even more to deposit samples, and you can do 5 tests simultaneously instead of manually dropping it 5 times, because you need to reduce the manual intervention. So this can we can play around with it and develop different strategies to improve the speed at which we can do the rapid diagnosis and extent of multiplexing. The other area where we can, and you can develop different types of flows. The other area, I'll just quickly wrap up in 5 more minutes, is and very important area is if we can use these capillary fluids or capillary flows to improve the performance of the face masks. Because after a lot of deliberation, even who now acclaims or rather admits that transmission. It's not only the mask, but the application can work also in wearable devices, detection devices like perspiration analyzer or fabric-based microfluidics. The second is what we can use on a mask, but I'll explain that in a short while. But talking about the masks, yes, masks are at present, it's internationally acclaimed that can lead to a reduction in the spread. More importantly, mask is not to prevent you, but the mask, you wear the mask to prevent others. And by what? By not only during the cough and sneeze, but also during exhaling. Generally, in a cough, the typical droplet size distribution microns, and beyond 100 microns, these droplets are ballistic, means that they have high inertia so that they are transported to a larger distance. The smaller droplets stay longer in the air, but they have a smaller tendency to deposit on a surface. So if you are walking through a cloud of smaller droplets, most likely they will penetrate or they will bypass you. They will only hit you, or when you inhale, they will be sucked in through your mask, and therefore in that time the mask as the arrestor of those tiny droplets. Studies have shown that by using a simple handkerchief you get some efficacy, which is better than at least using no mask, but you improve the performance by using homemade cotton mask or even commercial masks. Remember the basic precondition. These are some smoke viewing of artificial coughing and sneezing through a mannequin, and what is observed there is that there is a comparable amount of leakage through the gap between the mask and the wearer, which needs to be very carefully adjusted. I have seen doctors wearing N95 mask where there is a large gap between particularly around the nose, between the skin and the mask. It's as ineffective as wearing a very bad mask. That has to be taken into consideration. Not only very recent study, even studies as old as conducted in 2009 during the outbreak of the swine flu, people have conducted studies and seen that there is considerable amount of leakage past the mask or between the face, skin and the mask, which needs to be contained. And also, that's in all the cases, it's better than wearing no mask. The transport of liquid through mask takes place through permeation of the liquid droplets through a porous medium. So if we consider this as a porous medium, the flow should take place through the porous medium. It's a typical Darcy flow, where there is a pressure drop, and the pressure drop is related to the permeability and the viscosity of the fluid. Higher is the viscosity, the pressure drop is more, and it's more difficult to breathe. But at the same time, there is the porosity of the permeability of the fiber is also important. Remember, when you have droplets, the droplets pass through these pores of the mask, and when it permeates the liquid, the droplets, they absorb on the surface. There is condensation, there is re-evaporation. The virus, they tether or adsorb on the surface. There is desorption. It's a very complicated process, and the physics is very intricate. So if one has to really see what's happening inside a mask, it is a very rich field of study. But even going without those details, what we can see is that when a droplet hits a mask surface, there are few things that on a porous surface, the droplet experiences wicking, which is basically how the liquid transmits through a porous medium. And also there is a capillary pumping, which we have seen in case of solid surfaces. So there is a combination of capillary, Hemi Wicking, wicking and capillary pumping, and also the Darcy flow through a porous medium. All these take place through a mask. If we take a mask surface and treat any surface, for example, if we take a paper towel, a tissue paper, and make a surface, the top surface of it hydrophobic and the bottom surface as hydrophilic, super hydrophilic, what we see is that initially the liquid is retained on the top, but slowly over time, the liquid permeates to the other side. So that is what is shown schematically. A droplet falls on the surface. It's initially held up like a bead, but finally it permeates to the other surface. But if we design the surface, or rather if we make the top surface super hydrophilic and the bottom surface super hydrophobic, the strange thing is that you deposit a droplet, it spreads on the surface, it doesn't permeate to the other side. And this is known as a fluidic diode phenomenon. So it's very important. You want to create a scenario where the droplet should not penetrate, then this surface should be hydrophilic, the other surface should be super hydrophobic. But at the same time, if you are wearing the mask, you don't want the droplet to be like sticking between you and the mask. So that is also kind of inconvenient. So we actually tried to develop a face mask based on the regularly or easily available materials. That was particularly developed in the initial phase of lockdown, when there was no, there was a very large scarcity of masks in the market. We prepared a 3-layered mask, which comprised of polypropylene layers, a pair of polypropylene layers which were hydrophobic, and an intervening layer which was prepared from a hydrophilic cotton layer. This actually was made up from gamcha, a hydrophilic cotton cloth, or even like a cotton t-shirt or vest, which was juxtaposed between a pair of polypropylene layers which were actually made up from the polypropylene bags which we get from stores. These polypropylene layers are non-woven fibers under a regular microscope. This was imaged at home using a small kids microscope setup, and we found that this hydrophilic layer gives us a water diode scenario. So a droplet falling on this is residing on this surface for a while, and it goes into the other side, and it is absorbed in the hydrophilic layer. But the outer hydrophobic layer, what happens is that it's the same water diode. Now it is a hydrophilic layer followed by a hydrophobic layer, so the droplet cannot penetrate to the outer side. So a high velocity water droplet after sneezing would penetrate this layer and will fall on this intermediate hydrophilic layer. But because of the water diode phenomenon, from hydrophilic to hydrophobic, it cannot penetrate. So we prefer to have this layer where the liquid transports through the inner hydrophobic layer, wicks into the intermediate layer, stays there, but no penetration. This is during coughing and sneezing. An analysis showed that if we have the fibers of this hydrophobic layer, we see the cross-section of the fiber, and a droplet impinges on a surface at a velocity u, then you create a dynamic pressure of the order of rho u squared. While the capillary force, because of the curvature of the meniscus, creates a resistive force, Pc, of the order of surface tension. This is the surface tension, cosine theta advancing by d4. This is the contact angle, advancing contact angle. This is the surface tension of the liquid, and this is the pore diameter, which is shown in the microscope. And if the pore diameter is of the order of 100 micron, we'll see that the droplet penetration will occur only if the velocity, the capillary, the driving pressure is greater than the resistive capillary pressure, which is, if you do the maths, if the velocity u is greater than root over of sigma cosine theta a by rho d4. If you take water, for example, which has a density of about 1000 kg per meter cube, the water has a surface tension of 70 millinewton per meter and a d4 of 100 micron, then you have less than a meter of velocity which is held up by this spore. But when we are sneezing, the velocity of the droplets are exceeding that, which means that if you are wearing a mask and you sneeze, this droplet would pass through this, but the water diode would retain that. But at the same time, the mask, when you are inhaling, this mask would arrest any droplet from outside, because during inhalation, the velocity of air passing through this surface is less than this blocking velocity of 0.68, which is true, which means that any floating droplet would eventually be arrested on the outermost layer, preventing any ingress. So this is this 3-layer mask design we actually made available through Jadavpur University website, and there is a wing called CIST CAST, which is a Center for Advanced and Affordable Technologies, and it was made public, and people used in the initial phase prepared masks. The local tailors prepared those masks based on this 3-layer technology, and it provided enough precaution. But this, right now we have different sorts of masks, all the surgical and N95 masks are there. We can use this wettability engineering to take it further, make the mask smart. Can we, for example, use a diagnostic patch on the mask? For example, if we have a regular mask and make a part of it wettable, by using wettable tracks on the underside, so that this liquid saliva or the breath figure that actually accumulates on the mask from the patient can be collected on a particular region, which acts as the detection pot. For example, if we use a track on a mask layer, meaning that the top layer of the mask is hydrophobic, but the bottom layer is hydrophilic, and we create a track on the other side of the mask, and any droplet falling on this side, if it can be transported to the other end. Now, forget about this case 2 and 3, I'm not going to discuss, but what it means is that we have a mask layer which is hydrophobic to the side of the wearer. By the water diode principle, if the other side is hydrophilic, there is a track design which is hydrophilic, and if you cough or sneeze on this, the droplet will fall on this side, it will permeate to the bottom side, which is shown here, and a track design of widening angle, or rather widening track, will transmit the liquid to the wider side, as we have seen on an open surface, and then transmit the liquid to the other side. What we can then achieve is a transmission, a vertical transmission through the porous medium, as well as a lateral transmission through the porous medium. Our study showed that yes, we can achieve that when we deposited a droplet on a paper towel, which is made super hydrophobic on this side. The other side has a channel which is super hydrophilic. So this dotted line shows the existence of a channel, and actually you see it from the top. The liquid is dispensed on the top surface is dry, but see on the bottom side, the liquid permeates to the lower side and it transmits to the other side. For those who have missed the action, I'm repeating it again. So the liquid is dispensed here, it permeates to the bottom of this paper towel, and there is a track which is hydrophilic. Through that track, the liquid permeates to the far end and it accumulates there. So there is a vertical transmission through the paper and a lateral transmission along the paper. Look at the other side of the paper. This top side is totally dry, but on the other side, the bottom side is accumulating the liquid. So, and the math shows that this accumulation time, basically, we can calculate how long it will take for a given volume of liquid to accumulate at the back end, and what shape and size of the track we need to design. But the bottom line is that on this mask, if we, on the inner side, or rather, sorry, the intermediate side of the hydrophilic region, if we can draw tracks like this, and you are sneezing and coughing everywhere on the mask, it can accumulate the liquid in the intermediate hydrophilic regime. And if we can integrate the a sensor which can detect the presence of the antigen or the S protein or the M protein of the virus in this sample using the liquid accumulated here. Of course, there will be a protective cover on the other side of the mask. You can develop a detection system which is worn on a mask. So a patient in a hospital, in a ward where, or in a containment or a quarantine center, if they are wearing this mask 24/7 and there is a detector which can give an electronic signal or simple colorimetric detection, can tell that their initial screening or do the initial screening that this patient is perhaps infected with the virus. That can actually cut the load of the actual detection, because right now the challenge is to reduce the burden on the PCR testing, which has a finite capacity. Actually, the possibilities are limitless, and it all needs your imagination to trigger to apply or deploy this knowledge of surface science to n number of areas. I would like to thank my team at Jadavpur University for this fog harvesting, condensation, and the wettability engineering approaches or rather studies, and also my collaborators at the University of Illinois, Chicago, and my collaborator at Department of Chemistry in Jadavpur University for whatever work we have done so far. And any of you who are interested in the long run, want to intern in my lab are welcome, and you'll get enough freedom to play with these fluids and this microfluidics and the surface phenomena. And I thank you very much for your patience, and also Maitri and Obijit for allowing me to speak in front of this bright young individuals. Thank you so much.
Thank you, Ranjan. It's a wonderful session, I should say. So a lot of possibilities, as you have mentioned the way it can really in near future maybe solve so many problems that we are facing these days for the COVID.
Absolutely.
Yeah, so Maitri, now the session we could keep it open for the participants to ask questions. Yeah.
Yes. Thank you, Ronnie. Excellent lecture. Because
Thank you.
It's very much application value is very high. And I also listened to all the lecture and that's excellent.
My pleasure.
Now I encourage the students, if you have any questions, please do it.
Yeah, from the participants, is there any question right now?
And I mean, you can ask in English or in Bengali. I can speak Bengali.
Exactly. Right,
So,
right.
language is
যাদের প্রশ্ন আছে তোমরা you can either type এখানে টাইপ করতে পারো অথবা জাস্ট আনমিউট করে নিজেকে প্রশ্ন করো আমি till then yes
আমি সায়ন চক্রবর্তী আচ্ছা স্যার আপনি ওই যে টেস্ট কিটের কথাটা বললেন যেটা ওই ক্যাপিলারি অ্যাকশনের মাধ্যমে তিনটে স্পট যদি পাওয়া যায় তো সেক্ষেত্রে আমরা বুঝতে পারবো আইজিজি আইজিএম দুটোই উপস্থিত আছে এই টেস্ট কিটটা কি এখন কমার্শিয়ালি অ্যাভেলেবেল
এই টেস্ট কিটটা তোমরা যদি খবরের কাগজ দেখে থাকো এই টেস্ট কিটটা বোধহয় মাস দেড়েক দুয়েক আগে এসেছিল বাজারে কিছু এবং সেগুলোতে কিছু সমস্যা দেখা দেয় স্পেসিফিসিটি অ্যান্ড সিলেক্টিভিটি যেটা আমি বলছিলাম সেইগুলো নিয়ে সমস্যা দেখা দেয় অর্থাৎ ফলস পজিটিভ এবং ফলস নেগেটিভ বড্ড বেশি হচ্ছিল তার কারণ ছিল ওই যে রিয়েজেন্ট গুলো ওই টেস্ট কিটে আগে থেকে জমিয়ে রাখা দরকার সেইগুলোতে কিছু গন্ডগোল ছিল ফলে ওই টেস্ট গুলোকে আবারও বন্ধ করে দেওয়া হয়েছিল আবার খুব সম্প্রতি শুরু হয়েছে এই র্যাপিড টেস্টিং ইউএসএ তে এই র্যাপিড টেস্টিংটা অলরেডি চালু হয়েছে অ্যান্ড বেসিক্যালি এটা অনেক জায়গাতেই চলছে আমাদের দেশে মাস ডিপ্লয়মেন্টটা এখনো আসেনি তবে আশা করছি যে খুব শীঘ্রই এটা মানে ইট উইল বি অ্যাভেলেবল
থ্যাংক ইউ স্যার আচ্ছা স্যার আরেকটা কোয়েশ্চেন ছিল সেটা হচ্ছে ওই আপনি যে কনডেনসেশনটা বললেন না যে হিউমিডিটি থেকে আমরা মানে ড্রিঙ্কেবল ওয়াটার পেতে পারি
একদম
একদম। তো সেখানে স্যার তার আগে আপনি ওই ওয়েনজেল আর ক্যাসিভেস্টারের একটা হাইব্রিড বলেছিলেন, যে ওই হাইব্রিডটা আমরা ইঞ্জিনিয়ার করতে পারি মেটাল সারফেসে। ওই হাইব্রিডটা কি স্যার কোনো ভালো ভূমিকা পালন করতে পারে ওই কনডেনসেশনের মাধ্যমে ওয়াটার কালেকশনে?
হ্যাঁ, দেখো তুমি খুব একটা ইম্পর্টেন্ট পয়েন্ট বলেছো। বেসিক্যালি আমি খুব ক্লিয়ারলি ওই হাইব্রিড কথাটা বলিনি, বাট গুড দ্যাট ইউ রেজ দ্যাট পয়েন্ট। ক্যাসিভেক্সটারে কন্ডেনসেশন হওয়ার সময় ক্যাসিভেক্সটারের লিকুইড ড্রপলেটটা খুব ইজিলি স্লাইড করে যেতে পারে, আর ওয়েনজেলে ওটা খুব জেদ্দি ড্রপলেটের মতো এক জায়গায় বসে থাকে। কন্ডেনসেশনের জন্য দুটোই কিন্তু বেস্ট অপশন নয়, কেননা ওই ক্যাসিভেক্সটারে ওর যে তলায় এয়ার লেয়ারটা থাকে দ্যাট অফার্স থার্মাল রেজিস্ট্যান্স, আর ওয়েনজেলে যেটা হয় ড্রপলেটটা কিছুতেই ওর জায়গা থেকে সরে যেতে চায় না, ফলে লিকুইডের রেজিস্ট্যান্স বাড়ে অথবা ক্যাসিভেক্সটারে এয়ারের রেজিস্ট্যান্সটা বাড়ে। এই দুটোর জন্যই কন্ডেনসেশন কিছুটা হ্যাম্পার্ড হয়। সো দ্য আইডিয়াল ইজ টু হ্যাভ partial wetting or hybrid wettings where ড্রপলেটের একটা জায়গায় ওয়েনজেল হবে যেখানে ইন্টিমেট কন্ট্যাক্ট বিটুইন দ্য সাবস্ট্রেট অ্যান্ড দ্য লিকুইড থাকবে, আর বাকি জায়গায় ক্যাসিভেক্সটার থাকবে, ফলে ড্রপলেটটা সহজেই ওর অরিজিনাল জায়গা থেকে ছিঁড়ে গ্লাইড করে অন্য জায়গায় যেতে পারবে। অর্থাৎ আইডিয়াটা হলো ড্রপলেট যেখানে নিউক্লিয়েট করেছে সেখানে ওয়েনজেল মোটে বড় হবে, কিন্তু ও যখন ফুটপ্রিন্টটা বাড়াতে থাকবে সেই জায়গায় ও ক্যাসিভেক্সটার মোটে থাকবে। এটা অনেকটা হচ্ছে তুমি একটা বেলুন ফোলাতে শুরু করেছো, বেলুনটা তোমার হাতে টেথার্ড আছে কিন্তু বেলুনটা গোড়ায় ছড়িয়ে পড়ছে। এই অবস্থায় যেটা হবে, একটুক্ষণ পরে ড্রপলেটটা যখন যথেষ্ট বড় হবে ওর ওজনে ও নিজে যেই সরে যেতে চাইবে, ক্যাসিভেক্স ওয়েনজেল পার্টটা যথেষ্ট ওকে টেথার করার জন্য ফোর্স দিতে পারবে না, ড্রপলেটটা ওখান থেকে ছিঁড়ে একবার বেরিয়ে গেলে ও ক্যাসিভেক্সটার মোডে গড়িয়ে পড়ে যাবে। দিস ইজ দ্য আইডিয়াল সিচুয়েশন অফ আ হাইব্রিড মোড অফ কন্ডেনসেশন।
Thank you, sir.
Thank you.
Good afternoon, sir. My name is Shubhantika Bose. Sir, in reference to the point that you raised about the mesh inline in cooling towers, sir, okhane apni bolechilen je if it's very hydrophilic, then what happens is that the mesh pores are clogged by water, which is detrimental to the cooling of the condensation of the water. But on the other hand, sir, later
no, it's not detrimental to the condensation. One, you have to keep in mind that when we are talking about the fog harvesting in cooling tower, the fogs are already condensed, so it is basically impinging the droplet or arresting the droplets in the liquid phase on the mesh. There is no condensation. Condensation is associated with a phase change where you need to provide cooling. So in a fog harvester, there is plain and simple mechanical intervention where the droplet deposits. So there is no condensation. You now carry on the question.
Yes, sir. So in the first part, you mentioned that if the material is hydrophilic, then the droplets within the cooling tower would be more attracted to it. But then, sir, later on, we understood that if the material is hydrophobic, then the water droplets itself, they can slide down better instead of dropping directly back into the base of the cooling tower.
Yeah.
So how is it that a balance is maintained in between the hydrophilic and hydrophobic qualities that this mesh requires? Because
Yes.
later on we learned that there were, in another feature that you mentioned, there were overlapping striations of hydrophilic and hydrophobic material. But how do we approach a same sort of solution for the mesh inline of a cooling tower?
A very intelligent question. Actually, we are actually still trying to figure out. The thing is that I mentioned in my slide one word which I didn't utter. It is mesh conundrum. It's really a situation where we cannot make the mesh highly hydrophilic, neither we can make it highly hydrophobic. Actually, the feature that we are demanding on the mesh is that the water will easily slide down the mesh, but it will not detach. Now, it's like sonar pathor bati. It's like you get a easy sliding means that you have a very low lateral adhesion, but it doesn't detach from the surface means it should have a high normal adhesion. Getting this balance is very tricky. Some of the the Teflon coating shows a favorable feature. For example, if you take a Teflon, a smooth Teflon, you find that the liquid droplet easily moves. You can move it very easily. You just take a piece of Teflon, put some droplet and blow over it, the droplets will easily move. But the contact angle is not very large, meaning that it's not apparently highly hydrophobic, yet it is facile on the surface. So that kind of surface can give you the desired optimum condition where it is hydrophilic in a sense that the contact angle is not very high, yet it has a low contact angle hysteresis so that it can easily slide down the mesh.
Thank you, sir. I understood.
Yeah, and at the same time, as you have said, the mesh should be made up of steel, and you do coating over it.
Yes, the mesh should be made up of steel to give you durability, and the coating has to be durable, because the moment you put a Teflon coating on it and there is continuous impingement of water over 24/7,
high impact is there.
It's gonna erode. So there is no easy answer to it.
And over and above, there is a dissimilar material interface between the steel and the Teflon.
Yes. So a Teflon is a low surface energy material, and you are trying to graft it on a high surface energy material. That's like, I mean, that itself is like problematic.
And do you do any kind of surface engineering over this coating Teflon?
So that for Teflon, the thing is that we had some initial trial with Teflon, and we burnt our finger that a Teflon just eroded. So what we are now trying is, we haven't, I mean, basically it's all stuck up. We have a project from ACRB and we couldn't yet start the work because of this lockdown. We are using basically an intermediate layer of the fluoroalkyl silane, or rather we are trying to use what, I mean, those who have seen, I mean, your household grills are painted, first they put a primer and then they put the paint. Why they do that? The primer is something which binds onto the metal as well as onto the paint. So generally the principle is, if you have a low surface energy material like the paint, it doesn't tether well with the metal. So that's why people put the primer. It's not that the primer is really, I mean, if you put a layer of paint instead of primer and the paint is more expensive, if you think that your grill will be more robust, that's not the case. So we try to put the primer like the fluoroalkyl silanes work as a very good primer. Like, I mean, they have they tether to the metal on one side, and the other side which repels water, they can attach to the paint. So we are gonna use that and try that out.
Okay. So any other questions from the অন্যান্য participants যারা রয়েছে কারো?
স্যার
আমার তো আরেকটা ইন্টারেস্টিং কোশ্চেন মনে হচ্ছে যে শ্রেয়সী বলো।
How does the surface tension affect the condensation on super hydrophobic or hydrophilic surfaces?
Surface tension of the liquid is important there, because a surface which appears hydrophobic to water, it may behave as a hydrophilic if you are condensing any other low surface tension liquid. There is an engineering shift to low surface tension liquid, because there is something known as, if you have a piece of pen and paper, you can write it down, organic Rankine cycle. If somebody is from mechanical engineering background or physics or thermodynamics, it's a new type of cycle where instead of steam or water, we use a refrigerant, and they produce very compact, highly compact power plants. So instead of water or steam, you get to use, or you use the refrigerants. And the refrigerants have much lower surface tension. So a surface which condenses steam in a dropwise mode can give film-wise condensation for a refrigerant. So there is a separate wing of research where people are trying to repel low surface tension fluid. So yes, a surface tension of the liquid plays a very vital role on the mode of condensation it will exhibit on a surface.
So to reach the film-wise condensation, can we have to start from droplet condensation?
Yes, generally, I mean, a film-wise condensation is not something that we like, but unfortunately, that's the destiny. So any condensation would start in a dropwise manner. Even on the highly superhydrophilic surface, there will be first nucleation spots. There will be tiny droplets growing, but now if the surface is superhydrophilic, the droplet will spread. And as the droplet spreads, it touches the other surface. So the formation of film is perhaps almost immediate. But if you see under high-speed camera, you will see a droplet dropwise in condensation for a first few hundred milliseconds.
Yes. Can we get the totally homogeneous nucleation?
If the surface is, see, the nucleation takes place on surface defects. If, for example, you superhydrophobic or hydrophilic surface, whatever you take, there are surface defects, and the surface defects on a homogeneously prepared surface, the surface defects are homogeneous. So in that case, there is a reasonable estimate that you can get homogeneous nucleation. But even then, it is statistically homogeneous. That doesn't mean that you will get synchronous growth of droplet. They will definitely be one larger and one smaller droplet.
Yes. So I have another question.
Yeah.
So can we perform any type of organic or inorganic reactions in a lab on a chip, which you determine?
Well, this is a tough question for me. I am not a chemist, and you said any type of reaction. Really, I will give it a pass because there could be other reactions which may not be feasible. But the idea is to have the relevant biochemical reactions take place on a lab on a chip. Generally, what happens is if you have an organic molecule, the reaction requires mixing, and large molecules need large diffusion time, and therefore you have to do mixing. And the lab on a chip devices therefore have to ensure some mechanism, separate mechanism to ensure mixing, because a lab on a chip device is very small. In a large beaker, what do? You put a magnetic stirrer. In a larger beaker, you put a mechanical stirrer. But in a lab on a chip device, you cannot have a spoon to stir the liquid. So there you have to do intelligent things to induce mixing. And I showed one such mixing where two droplets merged because of inertial sloshing. It created a mixing pattern.
Yes. Thank you, sir.
Mm-hmm.
Okay. And do you
I
have
think
any
a question করবে
স্যার একটা কোশ্চেন ছিল
বলো
স্যার আমি অর্পিশ মুখোপাধ্যায়
একটু জোরে
স্যার কোশ্চেনটা হচ্ছে নিউক্লিয়েশন জিনিসটা হয় কি করে
নিউক্লিয়েশন জিনিসটা হয় কি করে খুব ফান্ডামেন্টাল প্রশ্ন নিউক্লিয়েশনটা হলো একটা থার্মোডাইনামিক ঘটনা বেসিক্যালি ভলমার্স নিউক্লিয়েশন থিওরি একটা রয়েছে ধরো একটা ভেপার মলিকিউল রয়েছে ওর একটা নির্দিষ্ট এনার্জি রয়েছে আর তার কাছে একটা মেটেরিয়াল সারফেস আমি যদি হেটেরোজেনিয়াস নিউক্লিয়েশন ধরি সেখানে একটা মেটেরিয়ালের একটা স্পট রয়েছে যেটা কিনা ডিফেক্ট বলতে পারো এবার তুমি যদি ওই মেটেরিয়াল সারফেসটা টোটাল থার্মোডাইনামিক এনার্জিটা কনসিডার করো এবং দেয়ার ইজ আ মোমেন্ট যে যখন ওয়াটার ভেপার এনভায়রনমেন্টে রয়েছে দেয়ার ইজ কন্টিনিউয়াস বাইন্ডিং বম্বার্ডমেন্ট অফ দিস ওয়াটার ভেপার ড্রপলেটস অনটু দ্য মেটাল তো এই মলিকিউল গুলো যখনই ওখানে বম্বার্ড করছে ইট মোমেন্টারিলি ক্রিয়েটস an electronic system where you have the water as well as the not necessarily electronic it can be through hydrogen bonding also there is a situation where you have to consider the water molecules maybe a few molecules and the metal surface together এবং সেখানে প্রতি মুহূর্তে তুমি যদি এনার্জি ব্যালেন্স করো তাহলে দেখতে পাবে যদি এনার্জেটিক্যালি ফেভারেবল হয় তাহলে পূর্ববর্তী মুহূর্তে there was the bare metal in the next instance the energetically favorable condition will be the water the vapor in the liquid form means the metal and the liquid with a minimum critical radius যেটা কিনা নিউক্লিয়েশনের মিনিমাম রেডিয়াস হিসেবে আমরা we consider it as the minimum critical nucleation radius that is thermodynamically favorable. Conditionটা উল্টো দিকেও চলে যেতে পারে. It's a reversible reaction. So any moment you have the minimum critical radius, in the next moment you see that the entire water has flashed away. That is also possible. But generally condensation এর সময় কি হয়, since the metal temperature is somewhat lower, the Gibbs free energy will give rise to a condition where the total energy is minimized when you have the metal and a small hemisphere of the liquid. I mean H2O in liquid state. That is the origin of the nucleation.
তার মানে নিউক্লিয়েশন হওয়ার জন্য একটা ইমপারফেকশন থাকা নেসেসারি?
Not necessarily true, because homogeneous nucleation হয় জলের মানে সারফেসের উপরও নিউক্লিয়েশন হতে পারে, সেটাকে বলে হোমোজিনিয়াস নিউক্লিয়েশন। নিউক্লিয়েশনের ভলমার্স থিওরিতে একটা কন্ট্যাক্ট অ্যাঙ্গেলের এক্সপ্রেশন থাকে। জলের উপর জলের নিউক্লিয়েশন হলে সেই কন্ট্যাক্ট অ্যাঙ্গেল বিহেভস অলমোস্ট 180 ডিগ্রি, সো অ্যাজ ইফ the water surface repels the nucleation of the next water vapor molecule, যেটা কিনা একটা মেটাল সারফেসে কন্ট্যাক্ট অ্যাঙ্গেলটা অনেক কম, সেক্ষেত্রে it has a much higher nucleation propensity. The energy barrier for a heterogeneous nucleation is much lower than that for a homogeneous nucleation.
আচ্ছা,
এবং এগুলো ওই অনেকটা আর্হেনিয়াস টাইপ রিঅ্যাকশন হয়, তো ফলে ওই এনার্জি ব্যারিয়ার টার্মটা থাকে একটা এক্সপোনেনশিয়ালের উপর চড়ে, ফলে এনার্জি ব্যারিয়ার ডাবল মানে অ্যাকচুয়াল নিউক্লিয়েশন রেটের অনেকটা ডিফারেন্স হয়ে যায়। এনার্জি ব্যারিয়ার 10 গুণ মানে বুঝতেই পারছো e⁻10 টাইমস এর গল্প, ফলে ওইটা একটা ইম্পর্টেন্ট রোল প্লে করে।
থ্যাংক ইউ স্যার।
ওকে, থ্যাংক ইউ। Are there any other question?
Sir, I have four follow-up questions.
Yeah.
Yes, sir. আপনি যখন discuss করছিলেন about the materials which are used in the mesh, then why do we use stainless steel and then cover it in a coating of Teflon when both the materials are of different nature? আর আপনি নিজেই বলেন যে stainless steel can erode. So why don't we use a more durable material, somewhat type of a polymer, which is a material which is similar to Teflon instead of using stainless steel? This is the first question, sir.
Okay, should I answer the first? Yeah.
Yes, sir.
So now I haven't mentioned that stainless steel can be eroded. The stainless steel was in a highly corrosive environment, we could etch the stainless steel, but in a regular scenario, the stainless steel, the primary reason for using stainless steel was the durability, because it's highly durable, and grafting so that's the reason of using stainless steel. Purely polypropylene mesh are also possible, and actually for atmospheric fog harvesters, people have used that, but generally they are vulnerable to rupture. Second question.
Yes, so the second question is that in cooling towers, sometimes with water, other liquids which have surface tensions or maybe melting points and boiling points similar to water itself can be present in that mixture. This is what I've read in some cases in which I think acetone and water had a mixture, or basically liquids which cannot be separated easily. So is it possible by any means for the cooling tower itself, by the use of the difference in surface tension, to separate those liquids so that more money and more resources are not invested in separating them later on?
So you are basically talking about preferential separation based on surface tension.
Yes,
when the surface tension difference is small and the fluids are miscible in nature, it's highly difficult. But people have tried, and with limited success, people have separated oil and water phases. Miscibility is an issue where, it's not the acid, you are talking about what liquid, if it's like chemical A and chemical B, both are soluble in water, you really do not get a distinct surface tension. You generally get a reduced surface tension when that is inseparable, and the liquids are inseparable from water. It's hard to separate, but insoluble or say oil phase and water phases can be separated using a mesh.
All right, sir. Understood.
Well, any other question?
Sir, I want to know some information. Do the mirrors of vehicle be super hydrophilic surface?
Yeah, the mirrors, if you have ever traveled in a bus and if it's under torrential rain, you might have seen that the driver suddenly disappears, stopping the car next to some bush and brings some kochu leaves and then smears it all over the windscreen. They try to make it hydrophilic so that the beads, the droplets do not appear as beads. So yes, the windshields and mirrors there are coatings available which makes it hydrophilic so that you don't have those droplets. There you don't want droplets. You want a nice film which almost gives like a droplet-free glass.
Yes. So why the self-cleaning glass was rubbish in the picture you defined in your slide?
What? Sorry, I didn't get your question.
Why the self-cleaning glass made of titanium dioxide? Most probably, it was the finest rubbish surface. Why
Finest? What do you mention? Finest
rubbish surface. It was not the smooth.
Oh, okay. Rough surface. Yes, it was not smooth. Yeah. So, what is the question?
Can it be smooth, or why it is rubbish?
Okay. So the necessity for roughness was to make it super hydrophobic. I didn't mention it. If say by chemicals means alone, if you have a surface, say a smooth glass surface, and you graft a layer of fluoroalkyl silane by some means on top of it so that it's repelling water, you get a contact angle close to 120 degrees. You cannot go beyond that. In order to improve the contact angle, you have to go beyond that, for which you need to make roughness features. The other importance of roughness is that then there is a chance of going into that Cassie-Baxter mode, where there is a layer of air entrapped and the water will keep bouncing on top of it without puncturing into the crevices or smearing on the surface. So the necessity of the surface roughening was to make the surface from hydrophobic to super hydrophobic.
Okay, sir. What is the relation of angle? I could not understand this.
The relation between the contact angle? The contact angle is, I showed in one slide the Cassie-Baxter mode, the contact angle, apparent and actual intrinsic contact angle. So suppose you have a surface, a Teflon surface, which is smooth, and you get a contact angle of 120 degree. And it has a contact angle hysteresis. And now you take the same sample and make it rough by some means. You will find two things. One is that the contact angle increases, so it is now more agile. And because of this roughness, it is in the Cassie-Baxter mode. So it becomes more like on a lotus leaf, the water droplet can shed. So the roughness was imparted to increase the contact angle and reduce the contact angle hysteresis so that the water can easily be picked up from the surface, or rather it can be easily dislodged from the surface.
Yes. Okay, thank you, sir.
Mm-hmm.
Well, so we are already running out of time, and would you like to now maybe conclude the session? And my one query is that যেটা আপনি বললেন শেষের দিকটাতে একদম যে ওই যে ডিটেক্টিং মাস্ক, প্র্যাকটিক্যালি মাস্কের ভেতর থেকে যদি আমরা ডিটেকশনটা করে ফেলতে পারি, is there anybody who has already started work on it?
আমরা চেষ্টা করছি, সেটা একটা প্রপোজাল লিখছি। তো
সেটা কি বাই সাম কাইন্ড অফ লিথোগ্রাফি ইত্যাদি দিয়ে প্রিন্ট করছেন মাস্কের উপরে?
না, এটা ওরকম কিছু না। আমাদের যেটা প্ল্যান সেটা হচ্ছে যে খুব সিম্পল, বেসিক্যালি একটা নন ওয়েটেবল লেয়ার অফ ফেব্রিক, তারপরে একটা তার মধ্যে যদি একটা ওয়েটেবল লেয়ারকে স্টিচ করে দেওয়া যায়, এমব্রয়ডারি,
Right.
তাহলে ওই ওয়েটেবল মানে হাইড্রোফিলিক থ্রেডটা দ্যাট ক্যান অ্যাক্ট অ্যাজ আ চ্যানেল ফর ট্রান্সমিটিং দ্য লিকুইড।
Okay, will it work? মানে টেস্টিং
Well, I mean, we have to see. কেননা ওই আমি আমার স্লাইডে ওটার মেনশন করেছিলাম। I mean, there is a company called Achira Lab based in Bangalore, যারা কিনা মাইক্রোফ্লুইডিক্স এর উপর কাজ করে। ওদের সিইও যে ধনঞ্জয় ডেন্ডুকুরি নাম, হি ইজ অ্যান MIT PhD। ওদের কিছু কাজ ছিল ব্যাক ইন 2010-12 I guess, মানে they have a discontinued that work, but ওরা ওই আমাদের যে তাঁত রয়েছে না, সেই তাঁতের টেকনোলজি ইউজ করে they were making lab on a chipের জায়গায় lab on a fiber, so basically textile based lab on a chip device. So you deposit a droplet on a super hydrophobic fabric, and there is a small section where you have a super hydrophilic thread on it. The water is transported, so it is demonstrated. Now whether it will work with the tiniest droplets in breadth figure is a question, and we need to verify
and
that.
the nature of the thread you are using, right?
So unless we work on that, we don't know.
Okay, so we all should be looking at that as
Yeah,
fast as it comes out.
The situation is such that when we need the labs most, the labs are closed.
Absolutely, that's the problem.
So the mask that we fabricated, actually it was all done at home, means like the contact angle measurement and everything. My son helped me with his DIY microscope kit and USB camera, everything. There was another faculty who used a garden sprayer to see the efficacy of the mask. And I'm telling this in front of these kids also, students also, you can do a lab at your home even now and develop things.
Absolutely. So I now request Professor Bhattacharya to conclude the session and conclude this seminar for today.
Yes. আমার মনে হয় আজকে প্রফেসর গাঙ্গুলি যে আলোচনা করলেন তাতে শুধুমাত্র আমাদের স্কলার স্টুডেন্টসরাই নয়, আমি আর অভিজিৎও খুব সমৃদ্ধ হলাম। মানে খুব ভালো আলোচনা হচ্ছে, আমাদের ভীষণ মানে ভালো লেগেছে। আর সব থেকে ভালো লেগেছে যে ছাত্ররা যখন কোয়েশ্চেন করেছে, প্রফেসর গাঙ্গুলি এত বেসিক লেভেলে গিয়ে পুরো ফিজিক্সটা বুঝিয়ে এত সুন্দরভাবে ওদেরকে ইন্সপায়ার করেছেন। I think it's a very good discussion.
That at the end of the third hour, 3 ঘন্টা চললো।
Yeah. Thank you for your patience.
খুব ভালো লেগেছে।
So interesting. আমরা বুঝতেই পারিনি।
একদম। আমরা আগামী দিনে আবার ওনার কাছ থেকে আরো অন্য কোনো একটা বিষয় শুনবো নিশ্চয়ই, কারণ আজকেরটা এত ভালো লেগেছে যে আবার ইচ্ছে করছে শুনতে।
Sure. My pleasure.
থ্যাংক ইউ ভেরি মাচ। উনি নিশ্চয়ই খুব টায়ার্ড হয়ে গেছেন 3 ঘন্টা পুরো। তবে আমাদের স্কলাররাও এত উৎসাহ করে শুনেছে, আর এই যে কয়েকজন যে কোয়েশ্চেন করলো এত মানে প্রত্যেকটা খুঁটিনাটি জানতে চেয়েছে, সবাইকে
That was impressive.
এক্স্যাক্টলি। অনেক অনেক ধন্যবাদ প্রফেসর গাঙ্গুলি আমাদের সঙ্গে।
সবাই সুস্থ থেকো, ভালো থেকো, and keep innovating because that doesn't see any lockdown. তোমাদের বুদ্ধিতে চিন্তা ভাবনায় যেন কোনোদিন লকডাউন না হয়। You all will reach heights.
একদম ঠিক কথা, একদম ঠিক। থ্যাংক ইউ ভেরি মাচ, থ্যাংক ইউ ভেরি মাচ।
Okay, my best wishes.
একদম।